You're not trapped on Earth, you're trapped inside a distance problem so violent that even light can't outrun it. Most of the universe isn't just far away, it's being carried away faster than any message could ever follow. So what if the real horror of space isn't what's out there, but what you can never ever reach, no matter how long you wait? Look up, and the night sky feels crowded, yet almost everything in it is an absence pretending to be scenery. What terrifies is not what space contains, but what distance quietly forbids. In daylight, distance behaves, roads end, coastlines meet, and maps still promise arrival. In space, distance becomes a verdict, because every meter is paid for in time, energy, and delayed cause. The universe does not merely place things far apart, it enforces separation with rules that never negotiate. Even our nearest neighbours are not neighbours in any ordinary sense, only signals, arriving late, carrying a past we mistake for presence. This film is about that mismatch between intuition and reality, where the brain insists on over there and physics answers not anymore. We will treat light years as waiting rooms, not measurements, and learn why a simple command becomes prophecy once the gap is wide enough. We will watch the solar system stretch into a cold bureaucracy of units, astronomical then interstellar, until numbers stop behaving like numbers. Somewhere along the way, the familiar romance of exploration turns clinical, then unsettling, as distance reveals itself as a kind of architecture. We begin with a small, brutal thought experiment, an everyday world interrupted by a delay no one can feel, and no one can outrun. From there, we ride outward with the most distant artifacts our species has launched, listening as their voices thin into a mathematical whisper. Past the last dominance of the sun, leaving becomes a layered idea, border after border, each one real in consequence, none of them a clean escape. Then the Milky Way opens like a city designed to prevent meetings, stars spaced by years of light, neighbourhoods unsynchronized, histories out of phase. The galaxy's centre sits in darkness we can infer but not inhabit, and its spiral arms are not roads, but slow waves in a thin, haunted medium. Step farther still, and even the idea of direction begins to fail. Because between galaxies there are no landmarks, only depths you can't cross and timelines you can't align. Out there, structure returns in a form that feels almost biological. Filaments, nodes, and immense voids where nothing becomes a dominant feature. We will see how gravity and expansion sculpt a cosmic web, and how emptiness can be measured, mapped, and still remain psychologically ungraspable. And as the scale climbs, a final boundary emerges, not a wall you can touch, but a limit written into causality itself. Throughout this journey, we will keep one question in view. How does the universe's emptiness, combined with finite signal speed and relentless expansion, turn most of reality into something permanently unreachable? We will use the tools that let us measure what we cannot visit, and the language that keeps our awe from becoming denial. Because the deeper we look, the more the cosmos resembles an archive that is already closing, page by page, horizon by horizon. What you're about to see is not a tour of destinations. It is a guided encounter with the distances that make destinations meaningless. Distances so large that the mind keeps reaching for metaphors and keeps falling short. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From the solar system's slow exodus to the galaxy's unsynchronized provinces, we will follow distance until it becomes a hard limit. And when the horizon finally appears, you will understand why seeing is not the same as touching, and never was. Imagine Earth vanishes without warning, not exploding, just gone. No flash, no debris, no echo, only an absence where a world used to be. The oceans, the atmosphere, the magnetic field, the satellites, the radio chatter, the faint infrared glow of cities at night, all of it simply stops. The planet is not hidden behind dust or darkness. It is erased, and the universe is forced to catch up. How long until anyone could possibly know? Not suspect, not guess, but know through information that can travel. The answer is not emotional, and it is not philosophical. It is a clock built into the universe, and it ticks at light speed. In physics, changes do not propagate instantly, even when they feel immediate in daily life. The universe has a maximum update rate, and every observer lives inside that delay. If Earth disappeared, the Moon would keep orbiting for about 1.3 seconds. Then the orbit would fail because gravity's message would arrive late. That number comes from distance, not drama, about 384,000 kilometers divided by the speed of light. For a heartbeat, the Moon would follow a curve around a planet that is no longer there. This is where intuition breaks, because we think of gravity as a permanent tether. In modern terms, gravity is not a rope. It is a changing geometry of space-time, and the change travels. The sun would keep shining on empty space for about 8 minutes. Every sunrise in that window would be a delayed broadcast from a world already erased. The photons that warm your skin left the sun long before they reached you, and they would keep arriving on schedule. Even the blue of the sky would persist briefly, until the scattering air is gone and the light has nothing to bloom against. For anyone farther out, Earth would persist as a ghost image, a planet that exists only because the news has not arrived. A telescope near Saturn would still see Earth's pale dot in the right place, and a probe beyond Neptune would still feel Earth's gravity for hours. In that interval, the universe contains two versions of truth, separated by distance. This is the first lie we tell ourselves about space. We say space is just up there, like a ceiling you can reach. We inherit that lie from maps and classroom diagrams, where the solar system fits on a page. In those drawings, distance is a label. In reality, distance is a delay, and delay is a wall. Distance is not a number in a textbook. Distance is a barrier enforced by physical law, and the law does not negotiate. Light is the fastest thing we know, and it is still slow. It is a speed limit that turns separation into time. This limit is not a technical inconvenience, and it is not something we have outgrown. It is woven into causality itself. Events can influence only what their light or their gravity can reach. Every meter of space adds delay, and delay becomes isolation. Reality is not shared instantly, even inside our own system. Even the signals we call instant, like a radio ping to a spacecraft, are only light in a different costume. They travel at the same speed, and the same silence opens between question and answer. This documentary is built on a simple spine. Distance plus physical law equals isolation, and isolation is the universe's default condition. That isolation is not just emotional, and it is not just poetic. It is logistical, biological, and thermodynamic. Life is fragile, and space is a place where fragility has no mercy. Emptiness is not peaceful when you need to cross it. Emptiness is what prevents rescue, return, and even confirmation. In empty space, there is no air to carry sound and no pressure to slow a leak. Heat does not drift away gently. It radiates, and the balance between freezing and overheating becomes a constant engineering fight. We evolved to judge distances that fit inside a landscape. Our brains compress vast space into a picture, and the picture lies. Our perception was shaped by savannas, shorelines, and mountains, where far meant a long walk. The neural machinery that estimates risk and effort was never meant to handle millions of kilometers. We see the moon and feel it is close. We see Mars and feel it is a destination, like another continent. The moon hangs like a lantern, large enough to feel reachable, and Mars glows with a steady redness that suggests familiarity. But those impressions are artifacts of vision, not measures of difficulty. But the mind's intuition collapses when distance becomes time, when the gap is so large that even light must travel. The moment you translate kilometers into minutes, the solar system stops being a picture. It becomes a schedule, and every schedule implies waiting, uncertainty, and missed chances. So we need a primer that does not comfort us. We need units that admit the scale, even when the scale refuses to fit. An astronomical unit is the average distance from Earth to the Sun. It is about 150 million kilometers, and it is already beyond ordinary meaning. Historically, even that number was hard-won, because early astronomers had to triangulate the solar system from tiny shifts in angle. The AU is a reminder that space resists measurement as much as it resists travel. At 1 AU, sunlight takes about 8 minutes to arrive. That means every moment of daylight is already history, and our entire climate runs on delayed energy. A light year is not a measure of brightness. It is how far light travels in a year, and it is about 9.46 trillion kilometers. It is also a unit of patience, because it bakes time into the distance. When you say 4 light years, You're saying 4 years of waiting, even before you ask what is waiting for you. These are not just bigger rulers. They are reminders that space is mostly the interval between things, not the things themselves. The objects get the attention because they shine and cast shadows. The interval is what dominates the budget of travel, communication and survival, and it dominates by orders of magnitude. If Earth were a grain of sand, the Sun would be a larger bead several meters away. The nearest star would be another bead hundreds of kilometers distant. In that scale model, the planets are not arranged like a tidy row. They are specks lost in a hallway of emptiness, and the hallway keeps going long after the mind expects a wall. Analogies help, but they also fail, because they still happen inside a room. Space is not a room, and there is no wall. A room has air, friction, and a sense of enclosure, even when it is vast. Space has none of that, only vacuum, radiation, and trajectories that do not forgive small mistakes. The unsettling part is not the darkness. The unsettling part is that the darkness is distance, and distance is what you cannot bargain with. Darkness feels like something you can light, as if a brighter lamp would solve it. Distance cannot be illuminated away, because it is not a lack of photons, it is a lack of closeness. We start where we think we understand. We start in the solar system, our so-called neighbourhood, where the brain already misreads the map. The planets look like a line-up in a diagram. In reality, they are scattered islands, and most of the ocean between them is nothing. That ocean is not water, but it behaves like a barrier in the same way. It forces you to carry your own life support, and it punishes you for arriving late. Even the word nothing is misleading. The void is not empty in a friendly way, because it still costs energy to cross. There is no free coasting in the human sense, because you cannot refill, repair, or restock along the way. Momentum helps, but it does not provide food, oxygen, or shielding. To move through space, you must bring everything with you. Air, water, heat, power, shielding, and time, all paid for in mass. Mass is not just weight, and rockets do not push against air the way intuition suggests. They throw reaction mass backward, and the mathematics of that trade becomes brutal as distances grow. The farther you go, the more the distance turns into a survival problem. The universe makes travel expensive and it collects interest. Every extra day in transit multiplies risk. Radiation dose accumulates, systems degrade, and small failures compound. In spaceflight, time is not neutral. Time is a hazard. We have sent machines outward for decades, and they are still close by cosmic standards. Their journeys reveal how wrong our instincts are. On screen, a spacecraft seems to glide through a clean black sea, with stars fixed like pinholes. But the numbers underneath tell another story. Years of flight, tiny course corrections, and long stretches of radio silence. New Horizons launched in 2006 and reached Pluto in 2015. It took about 9 years to cross what textbooks often treat as the edge. It did not travel slowly by human standards, because it left Earth faster than any previous mission at the time. The distance is what made it slow, because distance turns speed into a calendar. Pluto was never the edge. Pluto is a waypoint, a marker that tells you how much farther the Sun's domain might extend. For most of the 20th century, Pluto carried the romance of a final planet, a last name on the list. Then we learned the list was never complete, and the edge was a story we told to make the map feel finished. At Pluto, sunlight is weak, and radio messages take hours to return. Even there, we're still inside the inner idea of home. Sunlight at Pluto is more than 1,000 times dimmer than at Earth, so the world is lit like permanent twilight. The spacecraft's radio signal, thin as a whisper, spreads out and fades as it crosses the void. Beyond Pluto is the Kuiper Belt, a region of icy bodies and dwarf worlds. It is not a boundary, it is a thickening of distance. The Kuiper Belt is a fossil field of early solar system debris, cold enough for water ice to behave like rock. Each object is a time capsule, but the capsules are scattered so widely that region is almost too tidy a word. The solar system does not end where the pictures stop. It ends where the sun's influence fades into the galaxy, and that fade is enormous. Influence here means gravity, but also the subtle dominance of the sun over the trajectories of small bodies. Far enough out, the galaxy's pull and passing stars begin to compete, and the sun's authority becomes negotiable. To understand that, we have to introduce a frontier we have never seen, a structure that exists mostly as inference. It is called the Oort cloud, and it is not a ring you can point to. It is a vast reservoir of icy objects surrounding the Sun. The idea dates back to the mid-20th century, when astronomers tried to explain comets that arrive from every direction. Jan Oort proposed a distant spherical swarm, an elegant answer to a messy observation. Some models place its inner edge thousands of astronomical units away. Some place its outer reach tens of thousands of astronomical units farther. Even the inner edge is so far that sunlight would take days to travel there, and a spacecraft would take centuries with today's propulsion. The outer estimates stretch the imagination until it becomes numb. In the most expansive estimates, the Oort cloud could extend close to a light year from the Sun. That is distance the brain cannot hold. If that is true, then the solar system is not a compact family of planets. It is a vast gravitational territory, thinning into a halo of frozen remnants that orbit in darkness for millions of years. A light year sounds like a star-scale unit, not a home-scale unit, yet the Sun's gravitational story may stretch that far into the dark. That story is written in orbital periods so long that human history is a blink against them. Some of those objects, if they exist as predicted, would complete a single orbit only after civilizations rise and fall many times. We have never directly observed the Oort cloud. No telescope has resolved its members as a mapped population, because they are too faint and too far. They would reflect almost no sunlight, and they would be lost against the star field, colder than any natural place on Earth. Even with modern surveys, the expected objects are needles, and the sky is an ocean. We know it the way you know a storm by the debris it throws. We infer it from long-period comets that fall inward from nowhere. Those comets appear suddenly, often with highly elongated orbits that suggest they started far beyond the planets. They are not regular commuters like Halley's Comet. They are rare visitors, arriving with the shock of surprise. Those comets arrive on steep, ancient orbits, as if nudged by passing stars and galactic tides. Their paths suggest a distant reservoir. A passing star does not need to come close to the Sun to matter at those distances. In the outermost reaches, the Sun's grip is weak, and small gravitational tugs can redirect an icy body toward the inner system. This is the theme of unseen distance. The regions that define our system are often not photographed places, but mathematical necessities. Astronomy has always mixed light with inference, because we cannot touch what we study. We watch how objects move, how orbits precess, how trajectories bend, and from those bends we reconstruct the invisible architecture. We draw maps from gravity, from perturbations, from rare visitors that cross the inner light. We build boundaries from effects, not from contact. In a sense, the solar system's outermost border is not a line, but a probability field. It is a gradual handoff from one gravitational ruler to another, and the handoff is messy. That should change how we think about the solar system. It is not a neat set of orbits, but a gradient of influence fading into uncertainty. The farther out you go, the less the system resembles a clockwork diagram. It becomes a fog of potential trajectories shaped by the Sun, the galaxy, and the random geometry of stellar flybys. When people say space is just up there, they imagine a short climb. They imagine that the hard part is building the rocket. Building the rocket is only the opening move, because propulsion is just one piece of the equation. Navigation, power, radiation protection, and sheer endurance become the true constraints as the distances lengthen. The harder part is that the destination is not simply far. The destination is separated by time, and time is a one-way cost. You cannot buy back the years spent in transit, and you cannot compress them without paying in energy. Even if you could accelerate hard, you would still face the problem of slowing down, because arriving is not the same as passing by. Light makes that cost visible. It turns distance into delayed reality, and delayed reality into a kind of loneliness. Loneliness here is not metaphorical, because it changes what is possible. It limits coordination, it slows decision-making, and it forces autonomy on explorers who cannot ask for help in the moment they need it. When we look at Jupiter, we see it as it was tens of minutes ago. When we talk to a probe near Pluto, we speak into hours of silence. That silence is not empty time, because spacecraft are still moving and systems are still changing. Commands arrive late, and the probe's reply is already history by the time it reaches Earth. Even inside our own system, we cannot have a real-time conversation across the full span. The solar system already breaks the idea of immediacy. In everyday life, conversation is feedback. And feedback is control. In deep space, control becomes prediction, and prediction becomes trust in machines that must act alone. And yet, this is still the easy zone, because the sun holds it together. The next step is where the lie becomes impossible to maintain. As long as the sun dominates, there is a shared centre, a common reference frame, a sense that everything belongs to one household. Beyond that, the household dissolves into separate addresses, each with its own gravity and its own time. If the sun's domain may reach a light year, then the next star is not nearby. It is an entirely separate island across an ocean with no bridges. The nearest stars are not neighbours in the human sense. They are other systems sealed off by distance that turns travel into generations. Even if you could travel faster than any spacecraft we have built, the journey would still be measured in years, not days. Meanwhile, the light that carries news and warning would enforce its own schedule, indifferent to urgency. So Chapter 1 ends with a shift in perspective. The solar system is not a small yard, it is a vast, mostly unseen territory. The familiar planets occupy a tiny inner clearing, brightly lit and frequently visited by our instruments. Around that clearing stretches a wilderness of cold orbits and faint objects, where the map is drawn mostly from mathematics. And if our own territory may stretch toward a light year, then the true horror is not what lies beyond. The horror is how little beyond can ever touch us. What does it mean to live in a universe where even catastrophe travels slowly, and where confirmation arrives after the event is already finished? What does it mean to call something near when near still implies years of delay? Next, we leave the sun's fading grip and measure the gap to the nearest stars. We test what nearby means when light itself needs years. We start with a machine that already feels like a myth, because it refuses to end. Voyager 1 is still moving, still transmitting, still carrying our fingerprints outward, an aluminum and gold artifact that has outlived its designer's careers. In wide shots, it is almost comically small against the black, a few meters of hardware swallowed by a sky with no scale. A dish antenna the size of a living room table catches sunlight like a pale coin. A long boom holds instruments away from the bus, and a power source fades like embers. Yet the deep space network still listens for its whisper, and the whisper still arrives. On screen, the signal is a thin spike pulled from noise, and the room is full of quiet concentration. The data rate is painfully low, measured in bits per second, but those bits are real. Today, Voyager 1 is about 23 billion kilometers from Earth, a number that sounds like departure. It sounds like victory, and it sounds like a clean break, but it is not freedom. It is distance without release, an outward drift that still belongs to something larger. Even the number itself is slippery, because Earth and Voyager are both moving. Sometimes the distance grows, sometimes the geometry changes, and the line between them is not fixed. In space, how far depends on when you ask, and from where. Because leaving the solar system is not one event with a ribbon-cutting moment. It is a stack of borders, each one larger than the last and each one more abstract. The first borders are drawn in plasma and sunlight, and the last borders are drawn in gravity and time. When people imagine an edge, they picture a wall, a final fence at the end of the map. Space does not give you a wall, and it rarely gives you a clean line. It gives you gradients, slow fades, and overlapping domains that only make sense on a graph. Voyager crossed the heliopause in 2012, and that date is real enough to mark on a calendar. The heliopause is the boundary where the solar wind finally loses its dominance, and the interstellar medium pushes back. It is a milestone, but it is not the sun's true edge. To understand why, we have to picture the sun not as a lamp, but as a machine. It is a star with a hot corona that leaks outward, and that leak becomes a wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing at hundreds of kilometers per second. That wind carries the sun's magnetic field with it, because charged particles drag field lines along. As the sun rotates, those field lines twist into a spiral, like a garden sprinkler pattern stretched across billions of kilometers. In diagrams, it looks tidy, but in reality it is turbulent and alive. In visuals, the heliosphere is often drawn like a comet tail, and that is not just artistic license. The sun moves through the local interstellar medium, so the bubble is compressed on one side and elongated on the other. Even our home, has a windward face and a downwind wake. Before the heliopause, there is a region called the heliosheath, where the solar wind slows and heats as it piles up. It is a kind of weatherfront in space, full of shocks and magnetic wrinkles. Voyager crossed that messy zone first, and only later reached the quieter change beyond. Crossing the heliopause means the wind thins and the plasma changes, and Voyager could feel it in numbers. Its instruments saw a drop in solar particles and a rise in galactic cosmic rays. It was as if a protective weather system weakened, and the harsher background of the galaxy became audible. Cosmic rays are not rays like light, but fast particles from distant explosions and violent astrophysical engines. They slam into detectors and leave signatures that look like tiny impacts. Inside the heliosphere, the solar magnetic field helps deflect some of them, like a loose shield. But that change is not the same as escape, and it does not mean the sun stops owning your orbit. It does not mean the sun's influence ends, and it does not mean you have entered a new jurisdiction. It means you are outside a particular atmosphere of charged breath, not outside the sun's domain. Gravity is not a fence you pass through, and it does not come with a sign. Gravity is a kingdom that fades, and it fades on scales our brains refuse to hold. The sun's pull weakens with distance, following an inverse square law, but it never snaps to zero. If you could watch the sun's gravity as a landscape, it would look like a broad, shallow valley. Near the sun, the slope is steep and planets hug their paths like marbles in a bowl. Far out, the slope becomes subtle, but it still tilts everything inward. Voyager is outside the heliosphere, but it is still deep inside the sun's gravitational territory. It is still falling around the sun, just on a long, open-ended path that will never circle back. Even now, the probe is part of the sun's story, not the galaxy's. That difference is the first prison bar, our habit of confusing a physical boundary with ownership. We confuse atmosphere with belonging, and we confuse wind with escape. We celebrate the heliopause because it is measurable, and we ignore gravity because it is patient. The second bar is older and darker, and it is mostly inferred rather than seen. It is the Oort cloud, the hypothesized halo of icy bodies that may extend tens of thousands of astronomical units. If it exists as models suggest, it is the solar system's farthest reservoir of debris. An astronomical unit is the average Earth, sun distance, and it is a comforting unit near the planets. Out here it becomes a counting system for emptiness, because the numbers climb into the thousands. The Oort cloud, if it is real, is not a ring but a vast sphere. We cannot point to the Oort cloud with a camera, because its objects are too small and too dim, and they are spread too thin. We infer it from long-period comets that arrive from every direction, on orbits that look like they were dropped from the sky. Their trajectories suggest a distant, roughly spherical source. Those comets are like messages from the deep freezer, preserved for billions of years in darkness. When they fall inward, sunlight wakes their ices, and they grow tails that can stretch millions of kilometers. The spectacle is brief, but the origin story is ancient. Historically, the idea took shape in the early 20th century, when astronomers tried to explain why some comets return on timescales longer than recorded history. Jan Oort argued that a vast cloud could be perturbed by passing stars and galactic tides, sending comets inward. The proposal was a bridge between observation and dynamics, an invisible structure demanded by the math. That galactic tide is not a wave you can see, but a slow gravitational stretching from the Milky Way itself. Over long times, the galaxy's mass distribution nudges distant objects, loosening some and tightening others. Even the solar system's far edge is not purely solar, it is shared with the galaxy. If the Oort cloud is real in the way models suggest, then home is not the planets. Home is a vast, cold reservoir of leftovers, bound to the sun by a gravitational thread so long it feels like fiction. The solar system, in that sense, is less a tidy family of worlds and more a diffuse ancient swarm. Voyager's speed is about 17 kilometers per second relative to the sun, and that number hides its own nuance. It is not accelerating anymore, and it is not powered flight, but coasting on momentum earned long ago. Its greatest speed boosts came from gravity assists, stolen politely from giant planets. Those flybys were like cosmic slingshots, using a planet's motion to reshape the spacecraft's path. The technique is elegant, and it is also a reminder of limits, because it depends on rare alignments. Voyager's era had a lucky geometry, a once-in-176 years arrangement that made the Grand Tour possible. At this pace, Voyager needs roughly 30,000 more years to fully clear the Oort cloud region, depending on where you draw the line. There is no official border post, no sign that says, "You are now leaving." There is only distance and the slow surrender of gravitational binding. Even the phrase "clear the Oort cloud" is a simplification, because the cloud is not a shell with a crisp radius, it is a probability distribution, thick in some regions and thin in others. Leaving it is less like crossing a gate and more like fading out of a fog. 30,000 years is not a travel time in the way we usually mean it. It is a mismatch between human meaning and cosmic distance, written in a number that refuses to fit in a lifetime. It is an interval that makes our calendars look like toys. Recorded human history is about 5,000 years, measured by writing and durable records. Agriculture is about 10,000 years, measured by domestication and settlement. Voyager's exit time makes both feel like recent inventions, like a short preface before the real story. If you overlay those spans on a timeline, the pyramids become a recent marker, not an ancient one. The Roman Empire becomes a flicker, and the Industrial Revolution becomes a spark. Voyager's remaining journey through the sun's debris halo keeps going, indifferent to every turning point. Imagine a timeline laid across a desert floor, with the first cities at one end and Voyager's departure at the other. The probe's remaining journey would stretch far beyond the visible horizon, past dunes and heat haze. The point is not the exact length, but the humiliation of scale. This is the emotional anchor of the chapter, and it is not just sentiment. A human artifact is already beyond the planets, beyond the familiar names, yet it is still not truly gone. It is like a stone thrown into an ocean that turns out to be a continent. Voyager is not a ship in the storybook sense, with rooms and corridors and a crew looking out a window. It is a message in a bottle, and the ocean is measured in millennia. The bottle does not know where it is going, and it cannot steer itself into meaning. It also carries a literal message, pressed into metal with the hope of being understood. The Golden Record is a curated artifact, sounds, images, and greetings, built on the assumption that curiosity might exist elsewhere. It is both humble and audacious because it admits we may never know. The probe's power comes from radioisotope thermoelectric generators, which turn heat from radioactive decay into electricity. Inside, plutonium-238 decays and releases heat, and thermocouples convert a fraction of that heat into usable power. The conversion is inefficient, but it is steady. That decay is predictable but unforgiving, so every year the available power drops. Engineers have had to shut down instruments one by one, choosing what to keep alive as the energy budget tightens. Each shutdown is a quiet goodbye, because there are no repairs and no second chances. Even communication is a kind of miracle at this range, and the physics is merciless. Voyager's transmitter is weak by modern standards, and its signal spreads as it travels, thinning into noise. The inverse square law applies here too. Every doubling of distance quarters the received power. On Earth, giant antennas and careful signal processing pull it back out, and the process looks almost like archaeology. Receivers integrate the signal over time, and computers compare patterns against expected codes. It is an act of patience that mirrors the mission itself. The obvious question follows, and it always follows. If leaving the sun takes longer than civilization, why not simply go faster? Why not build something that does not need 30,000 years to clear the outskirts? Speed is not only an engineering problem, and it is not only a materials problem. Speed is an energy problem that compounds with every extra kilometer per second. In spaceflight, velocity is purchased with energy, and the bill grows quickly. Rockets do not cruise on desire or on optimism, and they do not get discounts for ambition. They trade mass for velocity, and the trade is governed by the rocket equation. In plain language, you throw mass backward to push yourself forward, and the amount you must throw grows steeply. The equation is not just a formula, but a shape, a curve that punishes you exponentially. If your exhaust velocity is limited, then big speed demands a huge mass ratio. That is why rockets look like fuel tanks with a small spacecraft attached, because that is what they are. The intuition is brutal even without the math, and it shows up in every launch video. To carry more propellant, you need more propellant to carry that propellant. The vehicle becomes a stack of fuel whose purpose is to move more fuel, with the payload shrinking into an afterthought. Every added stage buys you speed by paying in mass, and the returns diminish. You can stage away empty tanks and engines, and that helps, but it does not break the logic. The deeper you push for delta V, the more the rocket looks like a compromise you can barely afford. Delta V is not speed itself, but a budget of possible speed changes. It is the currency of maneuvering, and it decides what missions can exist. When the budget runs out, you do not fail dramatically, you simply stop being able to choose. This is why distance is not the only issue, and it never has been. Energy is the hidden wall, and the wall gets taller the faster you demand to climb. The emptiness between worlds is not just space, it is the cost of changing your motion. Chemical rockets top out quickly, because chemical bonds store limited energy per kilogram. You can optimize engines, improve nozzle designs, and squeeze efficiency, but you cannot cheat chemistry. The energy density of chemical propellants sets a ceiling that engineering can only approach. Nuclear options raise the ceiling, but they do not erase the equation. With higher exhaust velocity, you can get more delta V for the same mass ratio, and that is real progress. Yet even then, the exponential nature of the trade keeps punishing ambition. There is also a practical reality that hides beneath the equations, and it matters for missions measured in decades. High-energy propulsion brings heat, radiation, and complexity has failure modes. A system that works on paper must also survive vibration, vacuum, and long silence. Then comes the second cruelty, the one that turns speed into a trap. Exploration requires not just speed, but control, and control means changing your velocity on demand. To arrive somewhere and study it, you must slow down, and slowing down in space is not free. Braking is just acceleration in reverse, and it demands the same kind of effort. If you bring fuel to brake, you must also bring fuel to bring that fuel. The rocket equation punishes you twice, once on the way out, and again when you try to stop. This is why the universe offers a compromise that feels like a taunt. You can pass through quickly, or you can arrive slowly, but arriving quickly is expensive in ways that scale violently. The dream of a fast, controlled arrival is where most concepts begin to break. This is relativity light, the everyday version of cosmic cruelty, and it arrives before the famous paradoxes. Even before time dilation becomes dramatic, the logistics already break human plans. Long before Einstein becomes a practical concern, Newton and Tsiolkovsky have already closed the door. Voyager's story shows the baseline, and it is a baseline written in hardware. We built a probe that can survive for decades, and it still needs tens of thousands of years to truly leave. The probe is a success, but it is also a measurement of how big home really is. Now we widen the frame. Beyond the Oort cloud is not a new neighborhood, it is interstellar space, and interstellar space is mostly nothing. It is not empty in the absolute sense, but it is empty in the way deserts are empty, vast, thin, and indifferent. Between stars there is gas, dust, and magnetic fields, but the densities are so low they defy intuition. A few atoms per cubic centimetre can count as a medium out there, yet even that thin material matters at high speed, because collisions add up over years. In visualizations, interstellar space is often shown as pure black, but the real scene has structure. There are wisps of dust, faint emission, and invisible fields threading through it. The emptiness is real, yet it is textured, like a dark ocean with subtle currents. The nearest star system is Alpha Centauri, a triple system bound by gravity. The nearest star within it is Proxima Centauri, about 4.2 light-years away. On a sky map it looks close, like a neighbour across the street, but the map is lying. A light-year is not a poetic unit, even if it sounds like one. It is a time delay baked into distance, and it is the universe's way of enforcing patience. A light-year is how far light travels in a year, and light is the fastest messenger we have. 4.2 light-years means light itself needs more than 4 years to cross. Any ship slower than light needs longer, and every realistic ship is slower by a humiliating margin. When you say nearest star, you are also saying nearest delay. With current spacecraft speeds, a Proxima mission would take around 70,000 years. The exact estimate shifts with trajectory and propulsion, but the order of magnitude does not. The number is not a prediction so much as a warning. 70,000 years is longer than cities, longer than writing, longer than the entire span of agriculture. It is longer than the time since the last ice age began to loosen its grip. It is a duration in which coastlines change, Languages fracture and nations vanish. It is also long enough for the night sky itself to rearrange, because stars move. Constellations are temporary drawings, and over tens of thousands of years they smear into new shapes. A probe launched toward Proxima is chasing a target that drifts. This is where interstellar travel stops being exploration in the familiar sense. It becomes archaeology performed by machines, with the archaeologists arriving after their civilization has become sediment. The mission is no longer a voyage, it is a cultural time capsule. A probe launched by one culture arrives to a star that has outlived that culture's language, politics, and memory. The builders become a rumour, then a footnote, then nothing at all. The spacecraft continues anyway, indifferent to the collapse of meaning behind it. Even if the probe works, its data returns late, and the delay is built into the geometry. The message arrives to descendants who may not recognise the question, or who may not have the infrastructure to listen. The receiver is part of the mission, and the receiver must survive. That is the second prison. Distance as time, not just distance as space. The gap between stars is a gap between eras, and it forces an uncomfortable question. Can a civilization stay coherent long enough to finish what it starts, without losing the thread? We can imagine a faster escape, and modern projects do, because imagination is what we have. Breakthrough Starshot proposes gram-scale nanosons pushed by a powerful laser. It is a concept that tries to dodge the rocket equation by leaving the propellant behind. The outline is simple, and that simplicity is part of its seduction. A light cell catches photons, and the photons deliver momentum without onboard fuel. The push comes from a laser array near Earth, operating like a distant hand that never touches the craft. In theory, the sail could reach a fraction of the speed of light, perhaps 20% if everything works. That changes the calendar from tens of millennia to decades, and decades are a human timescale. The proposal feels like a door cracking open, but the trade is immediate, and it is not subtle, because mass becomes the enemy. A tiny probe cannot carry heavy shielding, large instruments, or redundant systems. It must be minimal, because every extra gram demands more laser power and more acceleration distance. The acceleration itself is violent, and the visuals almost look like science fiction made literal. A thin sail must survive intense laser flux without warping, tearing, or tumbling. The beam must stay locked on target across enormous distances, because a small drift becomes a miss. At those speeds, interstellar dust is not romantic, and it is not gentle. A grain the size of smoke becomes a projectile with the energy of a bullet. The craft would need clever materials, clever geometry, and a lot of luck. Because the medium is thin, but the journey is long. Even gas becomes relevant, because at relativistic speeds, a sparse medium can behave like a sandblaster over time. Each impact is tiny, yet the cumulative erosion can matter across years. The mission becomes a contest between minimalism and survival, and the biggest trade is braking, the problem that returns like a refrain. A Starshot-style craft would likely not slow down at Proxima, because it has no propellant to spend and no obvious brake to deploy. It would not enter orbit, and it would not hover for close study. It would fly through at relativistic speed, and the encounter would be a drive-by. The closest pass might last seconds to minutes, depending on the trajectory and the target. The probe would have to collect images and spectra in a rush, while the scene whips past. That is not a visit, and the language matters because it reveals the compromise. It is a glance, a burst of data collected while the target becomes a blur. The dream shrinks into a single streak of measurements, like trying to understand a city by photographing it from a speeding train. Even the act of sending data back becomes part of the gamble. A gram-scale craft has limited power for transmission, and it must aim a tiny signal across light years. Earth must be listening at the right time, with enough sensitivity to catch a whisper under cosmic noise. The universe is designed for passers-by, not visitors, and that design is simply physics. It allows trajectories and it allows flybys, but it resists arrival. The physics does not forbid you from going. It simply makes staying there the expensive part. Even if you could go fast, you still cannot easily stop, and stopping is what turns travel into presence. Even if you could stop, you cannot easily bring enough fuel to do it again. The dream of interstellar travel becomes a chain of compromises that never quite closes. Speed demands energy, and energy demands mass, and mass demands more energy. The loop tightens until the mission becomes either tiny and fast, or heavy and slow, and neither option feels like the story we want. The equations do not care about narrative, only accounting. And while you argue with equations, the target itself changes. Stars flare, planets evolve, and atmospheres erode, and nothing waits for your arrival. The universe does not pause because you are travelling through it. Proxima has a planet in the habitable zone, and it is called Proxima Centauri b. It is often described as the nearest maybe Earth, the closest world that could in principle have liquid water. The phrase is tempting because it sounds like a second chance. But habitable zone is only a temperature estimate, not a guarantee of life. It is a calculation based on stellar brightness and orbital distance, assuming an atmosphere that can regulate heat. It is a first filter, not a verdict. Proxima is a red dwarf, and red dwarfs are active, especially when they are young. They flare, they spit radiation, and they can batter close-in planets with energetic particles. A planet in the habitable zone of a red dwarf must orbit close, and closeness has consequences. Those flares can strip atmospheres over time, especially if the planet lacks a strong magnetic field. They can also drive chemical changes in the upper atmosphere, breaking molecules apart and altering greenhouse balance. A world can sit at the right temperature and still be hostile. There is also the problem of tidal locking, which is common for close-in planets. One hemisphere may face the star continuously, while the other sits in permanent night. An atmosphere could redistribute heat, but if it is thin or damaged, the surface becomes extreme. So the nearest promising world becomes another disappointment framed as a question. It might be there, and it might be hostile, and it is still effectively unreachable. The maybe Earth becomes a maybe, twice over, maybe habitable, maybe visitable. This is the pattern the chapter is building, and it is not an accident. The closer you look, the more the universe withdraws, and the more it replaces romance with constraints. Each new detail is a reminder that nature does not negotiate. Voyager proves we can throw a small object outward and keep it alive for a while. It also proves that outward is not away, because away is not defined by a compass direction. Away is defined by whether you have escaped the binding forces that still claim you. The heliosphere is not the end, even if it feels like one, because it is only a plasma boundary. The Oort cloud is not a place you can hurry through, because your speed is a budget and your budget is physics. The nearest star is not a destination in any human time frame unless you accept radical compromises. The emptiness between stars is not just empty, and it is not just a backdrop. It is a schedule enforced by physics, and the schedule is longer than civilizations. It forces a strange thought. Maybe the galaxy is full of worlds that are effectively isolated, not by hostility, but by arithmetic. So we return to the central question, the one hiding beneath the numbers. How does the universe's emptiness plus the speed of a light turn most of reality into unreachable territory? How much of existence is visible and yet functionally out of reach? Here is one answer. Even our best outward sprint is still trapped inside the sun's long shadow, because that shadow is not darkness. It is gravity's reach, stretching far beyond where sunlight feels dominant. And if the nearest star is effectively unreachable, then the word neighbourhood becomes a lie we tell ourselves to feel less alone. We draw clusters on star charts and call them local, because we want the cosmos to resemble a town. But the distances do not cooperate. Next, we scale up again. If 4 light-years is already a wall, what happens when the wall becomes the galaxy? What happens when the distances we call local stretch into tens of thousands of light-years and the map becomes a maze of permanent separation? What happens when leaving home is not a chapter of travel, but a chapter of endurance, measured not in days or years, but in the lifetimes of cultures? The next step up is not another destination. It is a change in what distance means. In the solar system, emptiness is an obstacle between islands of gravity, and those islands still feel related. In the galaxy, emptiness becomes the architecture itself, an organizing principle, and the islands rarely touch. We call the Milky Way our home galaxy, as if home implies closeness and familiar routes. But a galaxy is not a neighborhood with sidewalks and shortcuts. It is a city built from addresses separated by light years, where the street grid is made of time. Start with the nearest stars and the illusion they create. On a sky map, points look packed together, like streetlights seen from far away through a humid night. The map compresses depth into a flat page, and the page lies, because the third dimension is where the real distance hides. Astronomers learned that lesson slowly, because the human eye is built for landscapes, not for parsecs. The ancient constellations were drawn as if the stars shared a single dome, and the pattern felt like a structure. Only later did parallax measurements reveal the truth. Those points are scattered at wildly different depths. The average separation between stars near the Sun is several light years, and that number is not negotiable. That is not a gap you cross with engines. That is a gap you cross with calendars, with generations, with the slow accumulation of drift. A light year is distance written as waiting time, a unit that turns motion into patience. Several light years mean several years for light, and longer for anything that carries mass. Even the fastest probe we have ever launched would need tens of thousands of years to reach even a handful of nearby stars. This is the first structural fact of the Milky Way. Stars are not clustered like houses on a block. They are scattered like buoys on an ocean that has no shore, and the ocean is so wide that each buoy feels alone. Between those buoys is not space, as a vague backdrop or a blank stage. It is a medium so thin that emptiness is the default state, and matter is the exception. The galaxy's luminous beauty is built on a foundation of near nothing. Interstellar space contains gas and dust, but the density is brutally low by any everyday standard. In many regions, you can count only a few atoms per cubic centimetre, and that still counts as a cloud. In the best laboratory vacuums on Earth, we work hard to approach conditions that the galaxy provides for free. Even where the gas is denser, it is not air in any familiar sense, and it does not behave like weather. It does not push back like wind. It does not carry sound because sound needs frequent collisions between particles. It barely exists, and yet it shapes everything over long times because gravity and radiation have patience. The gas is mostly hydrogen and helium, the leftover simplicity of the early universe, with traces of heavier elements forged in stars. Some regions are ionized into plasma by ultraviolet light, so electrons and protons drift separately through magnetic fields. Other regions are cold and neutral, where atoms can survive without being torn apart by radiation. Dust grains are rarer still, but they matter because they block and redden starlight. They also hide the galaxy from us, forcing us to map by inference rather than direct sight. A dust grain is tiny, often comparable to smoke particles, yet in the aggregate it becomes a veil across tens of thousands of light years. Visually, dust is something unsettling. It does not simply dim the view, it sculpts it, carving dark lanes through bright star fields like ink spilled across a photograph. In long exposure images, the Milky Way's glowing band is braided with shadow, and those shadows are not empty. They're crowded with obscuring grains. So the Milky Way is not a bright disk you can simply photograph and measure from the outside. It is a structure you reconstruct from partial information, from radio surveys, infrared light, and the motions of stars. Each wavelength is a different kind of flashlight, revealing a different layer of the same city. Radio observations can pierce dust, because long wavelengths slip between grains that block visible light. Infrared can also pass through many dusty regions, and it reveals cooler stars and warm dust that optical telescopes miss. Meanwhile, spectroscopy turns starlight into a barcode of motion, letting us measure how fast stars approach or recede. That uncertainty is not a footnote. It is part of the horror, because even the size of our own galaxy is not a clean number. We live inside the structure we are trying to measure, like trying to infer the shape of a forest while standing under its canopy. The Milky Way's diameter is often given as about 100,000 light-years, because that is a useful shorthand for the bright disk. Some evidence suggests it could be closer to 200,000 light-years when you include faint outer structure and the extended halo. The exact boundary depends on what you count as belonging and what you call the edge. The disk has edges that fade, not borders that stop, and that fading matters for intuition. Spiral arms are not rigid spokes, they are patterns, density waves that move through the disk and gently gather gas. The arms look like structures you could point to, yet they are more like traffic jams, regions where material lingers and lights up. The halo is even harder, a sparse population of stars and dark matter, whose shape we infer from gravity and stellar streams. Some halo stars travel on elongated, tilted orbits that ignore the neat plane of the disk. Their motions preserve ancient history, because the halo is partly built from smaller galaxies that were pulled apart and absorbed. We live inside this system, embedded in dust and looking through it, and that changes the entire experience of scale. Our view is like trying to map a city while standing in its fog, using distant sirens and traffic flow. You see hints of avenues, but the skyline is guessed. Yet even with uncertainty, the scale is clear enough to break intuition. A galaxy is not a collection you can hold in mind. It is a span of time measured in tens of thousands of years at light speed, and time is the one distance you cannot cheat. To feel that, imagine a message leaving Earth at the speed of light, perfectly aimed through the disk. To reach the far side of the Milky Way, it can take up to about 100,000 years, depending on the path and the galaxy's true extent. The message arrives as a relic, like a fossil pressed into the future. That is the best-case communication speed allowed by physics, and it is already unbearable. Anything slower turns that delay into millions of years, and the word conversation stops applying. A dialogue becomes two monologues separated by epochs. This is where the documentary's central question sharpens, because it stops being an engineering problem. Emptiness plus the speed of light does not just slow travel, it fractures reality into regions that cannot coordinate, even when they share the same galaxy. A galaxy looks like a single object in the night sky, and that appearance is the second lie. The Milky Way is not a unified place in any practical sense. It is a collection of isolated systems that only seem connected from far away, like a coastline that looks continuous until you sail it. The illusion is strengthened by light itself. When you look at the Milky Way's band, you are seeing a layered collage of distances stacked along the line of sight. Some of that light left its stars before humans built cities, and some left before humans existed at all. We can test that lie with a common intuition about galactic collisions. People hear that galaxies collide, and they imagine stars smashing together like cars in traffic. The metaphor is irresistible, because the images show two bright disks overlapping like paint. The truth is stranger and more ghostly. Galaxies can merge, overlap, and distort each other, and still have almost no direct star-star collisions. The event looks violent, yet the violence is mostly gravitational, like an invisible tide pulling at everything. The reason is the same reason the Milky Way feels empty. Stars are separated by light years, and stars themselves are tiny targets compared to those gaps. Even a star's extended atmosphere is a thin shell compared to the volume it occupies in the galactic sea. A star is enormous compared to Earth, but it's still a point inside a vast volume. If you scale the Sun down to a grain, the nearest star is still kilometers away in that model. The space between grains is the real story, because the grains almost never touch. So when two galaxies pass through each other, most stars simply thread the gaps, and the overlap is mostly transparent. They move under gravity's choreography, not through physical impacts. The galaxies interpenetrate like two swarms of gnats, sharing the same air without colliding. This is not a claim of safety, because safety depends on what you care about. The merger is still violent in another way because gravity reshapes orbits and compresses gas. A stable circular path can become elongated, tilted, or even flung outward into the halo. Gas clouds do collide because gas fills more volume than stars do, and gas cannot ignore pressure. When gas compresses, it can trigger bursts of star formation, and those new stars can change the galaxy's future. In some mergers, the central regions ignite with rapid starbirth, bright enough to outshine the quiet disk. The compressed gas also feeds central black holes, and that can light up a galaxy's core in high-energy radiation. Even if the stars mostly pass like ghosts, the gas behaves like weather systems meeting head-on. Shock fronts form, temperatures rise, and magnetic fields are twisted into new shapes. But the cinematic image of stars colliding is almost always wrong. The collision is a collision of gravitational fields and diffuse matter, not of stellar surfaces. The drama is written in tides, not in impacts. This matters because it overturns how we imagine density at galactic scales. A galaxy can look crowded and still be mostly vacuum, and vacuum is what enforces isolation. The bright parts are not the bulk, they are the highlights. Now bring in the future event that makes this real, because it gives the abstraction a date. The Andromeda Galaxy is on a collision course with the Milky Way, and the merger is expected in roughly 4 to 5 billion years. The prediction comes from careful measurements of Andromeda's motion relative to us, including subtle shifts in its light. That time is so long it feels like it belongs to geology, not history, and yet it is still a forecast. It is a reminder that even galaxies are not stable neighborhoods. They are temporary arrangements drifting through a larger cosmic web, pulled by gravity into slow encounters. As Andromeda approaches, the night sky will change over millions of years, not in a single catastrophic night. The two disks will overlap, tidal tails will stretch outward, and the combined system will settle into a new shape. From a planet inside the disk, the sky would gain a second luminous band, an approaching river of stars. Those tidal tails are not decorative. They are stars and gas drawn out by differential gravity, the same physics that raises tides on Earth, scaled up beyond comprehension. The galaxy's outskirts feel a different pull than its core, and the mismatch tears structures into arcs. Through all of that, individual stars will mostly never meet. Their trajectories will be perturbed, their neighbourhoods will change, but direct collisions remain extremely unlikely. A solar system might be nudged into a new orbit around the merged galaxy, while never seeing another star close enough to matter. So the Milky Way is both enormous and sparse. It is a city where nobody meets, even during the biggest traffic event the city can experience. The streets rearrange, the districts shift, and yet the citizens remain separated by the same empty blocks. That ghostly merger also exposes another truth, because it forces us to ask what actually holds a galaxy together. The main actor in a galaxy is not the stars you see. It is gravity, and much of that gravity comes from what you cannot see. Dark matter dominates the galaxy's mass budget, shaping the halo and the rotation curve, and it acts like an invisible envelope. We infer it from how stars orbit faster than visible matter alone can explain, especially in the outer disk where luminous mass thins out. The stars move as if they are embedded in a much heavier structure. This is another layer of mapping by effect, and it is a theme that repeats in every direction. We do not see the scaffold directly. We see the motion it forces, and we draw the structure from the motion. The galaxy is a diagram traced by orbits. Historically, this realization arrived as a shock, because it contradicted the expectation that light tracks mass. When astronomers measured rotation curves and found they stayed flat, they faced a choice: change gravity, or accept unseen matter. The modern picture keeps both possibilities in play, but the evidence for an unseen component is overwhelming. With that scaffold in mind, we can ask the question that sounds simple and becomes monstrous. Where is the centre of the Milky Way, and what anchors it? In a city, the centre is a place you can visit, but in a galaxy, the centre is a coordinate buried behind dust. The galactic centre is not a place you can point to with your eyes, even from the darkest desert on Earth. Dust blocks visible light along the plane, and the centre is crowded with gas, stars, and energetic processes. The region is a furnace of activity, but it is hidden behind a curtain. Yet we have a name for the anchor because radio astronomy can see what the eye cannot. Sagittarius A star, abbreviated Sagittarius A Yumd, is the compact radio source at the Milky Way's core. It is not a star at all, and the name is a historical artifact of early cataloguing. Sagittarius A is a supermassive black hole with a mass of about 4 million suns, and that number has weight. That number is not guessed from brightness. It is measured from motion, from the way nearby stars swing around an invisible point. We know because we can track stars orbiting the unseen centre, and the method is almost painfully elegant. Over decades, astronomers have mapped their paths with exquisite precision, watching them curve and accelerate as if pulled by a hidden hook. The orbits close in on a tiny region, implying an object both massive and compact. One star, often called S2, completes an orbit in about 16 years, which is astonishingly fast for something circling a galactic centre. At closest approach, it moves at thousands of kilometers per second, and its trajectory demands a compact object. The star's speed and curvature are a direct readout of the mass inside its orbit. The mass is too concentrated to be a cluster of normal stars, because such a cluster would betray itself. A dense cluster would be unstable and would emit light and collisions that we do not observe. The simplest explanation is a black hole, and the simplest explanation fits the data with brutal precision. This is a key beat in the documentary's logic, because it shows how knowledge survives distance. We cannot go there, but we can still know it is there, because gravity leaves fingerprints. In a universe that hides behind dust, motion becomes a kind of illumination. Sagittarius A is also a reminder of practical distance, because the centre is not just far in kilometres. The centre is about 26,000 light-years away from us, which means its light is 26,000 years old when it arrives. When we observe the region, we are watching a past that predates agriculture. Even if you could travel at light speed, reaching that anchor would take 26,000 years. At any realistic speed, it becomes a project longer than recorded civilization, longer than the lifespan of nations, longer than the continuity of most species. The destination exists, but it does not belong to human time. So the center is not a destination in the human sense. It is a coordinate, a reference point that organizes the map, while remaining unreachable in practice. We can plot it, model it, and orbit it, while never approaching it as travelers. That is the paradox of living inside a galaxy. You can belong to a structure you cannot traverse, and you can orbit a center you will never approach. The city contains you, but it does not grant you access. Now confront the phrase people use casually, as if it were a weekend plan: crossing the galaxy. At the speed of light, crossing a disk 100,000 light-years wide takes 100,000 years, and that is only the bright portion. If the Milky Way is closer to 200,000 light-years across in its extended structure, the crossing time doubles. Even the fastest possible messenger becomes a slow story. Those are not travel times. They are civilizational extinction windows, long enough for languages to die and species to diverge. They are long enough for continents to shift, for ice ages to come and go, for entire ecosystems to rewrite themselves. At 1% of light speed, which is far beyond our current capabilities, a 100,000 light-year crossing becomes 10 million years. At 0.1%, it becomes 100 million years. At that scale, the ship is not a vehicle, it is a geological process with a hull. Those numbers are not there to be dramatic. They are there to show what the speed limit does to ambition, and how emptiness turns ambition into archaeology. A mission becomes a ruin in advance because its builders will never see its end. Even if you imagine a ship that can survive, the galaxy still refuses to be a single community. The delay alone makes coordination impossible, because coordination requires shared context. By the time a plan arrives, the need has changed, and the sender has become a different world. A message sent across the Milky Way is a generational artifact, and its meaning decays while it travels. The reply arrives after the sender's culture is unrecognizable, or after it is gone. The exchange becomes asymmetrical, like finding a letter in a bottle from a vanished shore. So communication becomes something else, something colder and more archival. It becomes history exchange, a trade of fossils made of radio waves. You do not speak to a living partner, you receive an echo from a civilization that may already be dust. This is the isolation that hides inside the word civilization, and it is not a poetic complaint. A civilization is not just technology and cities, it is shared time, and shared time collapses when the delay is measured in millennia. Without shared time, even agreement becomes impossible. Within a few light years, you can still imagine a slow dialogue, like mail carried by ships across an ocean. Across tens of thousands of light years, dialogue becomes a museum exhibit. The only thing that can be shared is a snapshot, already outdated when it arrives. This is why the Milky Way is horrifying in a quiet way, and why the horror is structural rather than cinematic. It is not hostile because it attacks you. It is hostile because it does not allow togetherness at scale, and it does not care that you want it. Now return to the Andromeda merger with this in mind, and notice how the meaning changes. When galaxies merge, their stars mostly miss each other, but their societies would miss each other even more completely. The overlap of disks does not create intimacy. It creates a thicker fog of strangers. Even if intelligent life were widespread, the merger would not create contact in any ordinary sense. It would create rearrangement without meeting, and the distances would still enforce silence. Two civilizations could pass through the same merged galaxy and remain forever unaware, separated by time delays and empty volume. The galaxy is a social desert disguised as a glowing band, and that disguise is powerful. The light makes it look full, the physics makes it functionally empty. The beauty is real, but it is not an invitation. At this point, the mind searches for escape hatches, because the numbers feel like a locked room with smooth walls. Science fiction offers one word that sounds like a key: warp. In physics, the closest serious idea is the Alcubierre drive concept, which is both tantalizing and unsettling. It does not move a ship through space faster than light. It changes space-time itself, contracting space ahead and expanding space behind, so the ship rides a moving distortion. Inside the bubble, the ship could remain locally at rest, while the bubble moves, and that detail matters. The trick is not breaking the speed limit locally. The trick is bending the road, so the destination comes to you faster than you travel. It is a loophole written in geometry rather than propulsion. The catch is not a small engineering detail, and it is not something you can hand-wave away with better materials. The mathematics requires exotic matter, or negative energy density, a form of stress energy not observed in usable amounts. In plain language, the universe does not seem to hand out the kind of fuel the idea demands. Quantum field theory allows tiny negative energy effects in constrained situations, like the Casimir effect, and those effects are real. But those are minute and not obviously scalable to starship-sized space-time engineering. The gap between a tabletop measurement and a warp bubble is not a gap of effort, it is a gap of principle. There are also questions about stability and control, because a solution on paper is not automatically a vehicle. A warp bubble might be hard to start, hard to steer, and hard to stop without catastrophic energy gradients. Some analyses suggest it could create intense radiation hazards at the bubble's boundary, turning arrival into an impact. So the Alcubierre idea stays where it belongs for now, balance between insight and fantasy. It is a mysterious doorway drawn on paper, with no handle in the real world. It reminds us that space-time can be shaped, while also reminding us that shaping it may be beyond us. This is important to say out loud, because it keeps the tone grounded and the fear honest. The universe might allow loopholes, but we have not found one that can be built. Until we do, the speed of light remains the rule that turns maps into prisons. Without a loophole, the speed of light remains the hard boundary, and it does more than slow ships. It turns the Milky Way into a set of disconnected provinces, each living in its own delayed present. The galaxy becomes a mosaic of nows that cannot synchronize. Even within one spiral arm, the distances are large enough to make rescue meaningless, and that is a brutal thought. A distress call can travel for years before anyone hears it, and the event is already over. Help arrives as memorial, not as intervention. This is the same logic from Chapter 1, scaled up until it becomes existential. Distance is delay. Delay is isolation. Isolation is the default condition. The galaxy does not punish you, it simply refuses to compress. Now we tie the galaxy's structure back to the central question, because the structure is the argument. The universe's emptiness is not just between galaxies, it is inside galaxies. Inside the very thing we call a home, threaded through the places we imagine as connected. The Milky Way contains hundreds of billions of stars, perhaps more, and the number is genuinely staggering. That number sounds like abundance, but abundance does not imply access. A library can hold infinite books and still be locked. Most of those stars are too far to matter to each other in any practical time frame, and that is the quiet tragedy of scale. Their planets, if they have them, are light years away from the next possible harbour. Even if life is common, it is common in separate rooms. Even the stars that are close by are separated by years of travel at light speed, and that is the optimistic case. At human speeds, they are separated by lifetimes, and lifetimes are not enough. The nearest neighbours are still remote, and remoteness defines the culture of the galaxy. So the Milky Way becomes a lesson in scale that refuses comfort, even when the visuals are beautiful. It is vast enough to be impressive, and sparse enough to be lonely. The same emptiness that allows stable orbits also prevents connection. We can locate the centre, measure its mass, and model the halo, and those achievements are real triumphs of method. We can predict a merger billions of years away, and we can watch stars near Sagittarius A trace their tight loops. We can do all of that and still be trapped by the same limit. The opening hook returns in a new form, and it lands harder because we now have numbers. You're not trapped on Earth. You're trapped inside a distance problem that the galaxy itself cannot solve quickly. The prison is not a wall, it is a constant. A galaxy is not a community. It is a gravitational arrangement spread across 100,000 years of light travel, with a centre that is known yet unreachable. The Milky Way is a single object only in photographs, not in lived experience. And if a single galaxy is already too big to feel whole, then the next step is worse. The space between galaxies is where isolation stops being a challenge and becomes permanent. That is the transition forward. We leave the illusion that the Milky Way is a place you could someday cross, and we face the void that separates galaxies like islands in an expanding sea. The next chapter is not about another city, it is about the ocean between them. We leave the Milky Way behind in concept first because physically leaving is a different story. The galaxy was already a city where nobody meets, yet it was still one gravitational address. Its spiral arms were streets of light, and its dark lanes were the unlit alleys of dust. Even at our loneliest, we still lived inside a single rotating disk of shared gravity. Intergalactic space is what happens when even that thin sense of belonging dissolves. Visually, the change is almost insulting in its simplicity. Stars thin out, then the background turns quiet. The Milky Way's band fades from a textured river into a pale memory, and then into nothing at all. The familiar haze that once looked like weather becomes a hard black, like a screen turned off. There is no border marker, no wall, no last star that announces you have crossed a line. There is only the slow failure of density until here stops feeling like a place. The camera can linger on that thinning because it is how the universe hides its boundaries. A few bright stars remain, but they stop forming patterns that feel like home. The constellations distort as perspective changes, and then even distortion becomes irrelevant. Eventually, the sky is not crowded enough to suggest distance, only emptiness. The Milky Way is still behind you, but it no longer wraps the scene like a ceiling. Out here, even the Galaxy's halo feels less like a region and more like a fading influence. The last stray stars are not a wall, but a statistical tail, rare points in a distribution that finally runs out. The background becomes so uniform that depth cues vanish, and the mind begins to grasp for meaning. What does between mean when there are no mile markers and no nearby landmarks to triangulate? Start with the nearest external galaxy, because it is the only one most humans can see. Andromeda is a faint smear to the naked eye under dark skies, and it feels immediate. It sits near the limit of unaided vision, a soft spindle that looks like a cloud that forgot to move. To most eyes, it is not a billion stars, but a gentle bruise of light. For most of history, that glow was not a galaxy in the modern sense, but a puzzle. Ancient observers recorded it as a little cloud, and the label was honest in its uncertainty. The word nebula once meant almost anything that was not a sharp point of light. Early star catalogues treated it like a curiosity, a fixed stain on the dome of the sky. Telescopes sharpened it, and the smear became a structured object with a bright core. With enough aperture, its edges stopped being fog and started being geometry. Even then, the geometry was deceptive, because a spiral can be a nearby whirlpool or a distant continent. In the 19th century, astronomers sketched Andromeda as a luminous lens with hints of lanes, but its true scale remained unprovable. Photography helped by integrating light over hours, letting faint structure accumulate on glass. The longer the exposure, the more the cloud revealed itself as a system with internal order. In the early 20th century, the debate was fierce. Was it inside our galaxy or beyond it? The great debate was not about romance, but about scale and evidence. If Andromeda was nearby, then the Milky Way might be the whole universe. If it was distant, then the universe was filled with other Milky Ways, scattered beyond counting. The answer depended on distance, and distance depended on learning how to measure light itself. Andromeda feels close because the human brain equates visibility with nearness. That feeling is the trap, because the light is old before it reaches you. Even on Earth, you never see the present. You see a delayed signal processed by biology. Your retina integrates photons over fractions of a second, and your brain stitches them into now. In space, the delay is not milliseconds, and it does not politely stay negligible. Andromeda is about 2.5 million light-years away, which means its photons left 2.5 million years ago. When that light began travelling, modern Homo sapiens did not yet exist on Earth. Our ancestors were other humans, living with different tools, different languages, and different futures. Stone blades and firelight were the frontier technologies of that moment. The night sky above them contained the same faint smear, but it was an even older message then. The visual can make that time delay concrete. Ice ages advancing and retreating while the photons cross the dark. Continents shift by centimeters per year, yet over millions of years that becomes a rearrangement. Species appear, spread, and vanish while the signal is still en route. Andromeda's light is not a postcard from far away, but a postcard from long ago. The distance is measured in time because physics gives us no other honest unit. You can almost picture those photons as a thin, expanding shell, leaving Andromeda's disk and slipping into the void. They pass through the galaxy's own halo, then into intergalactic space where nothing guides them but geometry. Along the way, a few are absorbed, scattered, or redshifted by motion and gravity. Most simply, keep going. When they finally strike a telescope mirror, they complete a journey that began before our species had a name. What you see is not Andromeda now, because now is not a shared moment across that gap. The galaxy has continued rotating, forming stars and swallowing smaller companions while we waited. Its spiral arms have sheared and rewrapped, because differential rotation turns patterns into slow storms. Its supermassive black hole has continued its quiet accounting at the centre, whether active or not. Our view is a snapshot, and the shutter speed is measured in millions of years. Even the word snapshot is generous, because galaxies are not static subjects. Gas clouds collapse into clusters, then those clusters drift apart as their brightest stars die quickly. Supernovae seed the surrounding gas with heavier elements, changing the chemistry of the next generation. Dark matter halos keep the whole structure coherent, even when the visible disk looks delicate. Andromeda's present is a moving target, and our eyes cannot chase it. The arms themselves are not rigid things, but density waves, traffic jams of stars and gas that move through the disk. Gas enters the wave, compresses and forms bright, short-lived stars that outline the spiral for a brief moment. Then those stars die, and the pattern continues, indifferent to any single generation. When we admire the spiral, we're admiring a process, not a sculpture. This is the documentary's core mechanism in its purest form. Distance becomes time delay, and time delay becomes isolation that no technology can erase. Seeing becomes a kind of time travel, because the universe only updates at light speed. That speed is not a preference of physics, it is the wiring of space-time itself. The universe does not transmit reality instantly, because instantly is not a feature it offers. Light is an electromagnetic wave, and its speed is built into Maxwell's equations. Those equations tie electric and magnetic fields together so tightly that a self-propagating wave must move at a fixed rate. Relativity later made the rule deeper. No information outruns that limit without breaking causality. If signals could exceed it, effects could arrive before causes, and physics would lose its order. So every image is a messenger, and every messenger arrives late, even when nothing goes wrong. Across intergalactic distances, late becomes the defining feature of reality. The delay is not a technical glitch that better engineering will solve. It is the cost of having a universe with consistent cause and effect. Even gravity respects the limit, because changes in the gravitational field propagate at light speed. The cosmos is a network with finite bandwidth, and time is the price of every update. Even the word present becomes local, a private bubble around each observer. Your present is a thin slice of space-time around you, stitched together by signals that have arrived. Andromeda has its own present, and we can never look directly at it. We can only look at a historical record written in travelling light. The record is honest, but it is never current. That record is still valuable because it carries information about structure and motion. Astronomers measure Andromeda's distance through standard candles and calibrated brightness. The classic ladder begins with nearby parallax, then steps outward to pulsating Cepheid variables. Parallax uses Earth's orbit as a baseline, letting nearby stars shift against a distant background. Cepheids link period to luminosity, so their rhythmic brightening becomes a ruler made of time. This method has a history, and it is worth feeling its human scale. Henrietta Leavitt discovered the period-luminosity relationship while studying variable stars in photographic plates. Her work turned flickering points into a measuring tool, and it did so without needing to touch them. Later, Edwin Hubble used Cepheids in Andromeda to show it was far outside the Milky Way. The universe did not change that day, but our map did. Beyond that, other candles, like certain supernovae, extend the scale into deeper space. Type ER supernovae are especially useful because their peak brightness can be standardized after careful calibration. Each rung must be calibrated, because a small error nearby becomes a large lie far away. This is not abstract bookkeeping. It is how we learned Andromeda is truly external. Hubble's measurements helped end the island universe argument, and the cosmos expanded overnight. They measure its approach through Doppler shifts, reading velocity from displaced spectral lines. A spectral line is a fingerprint, a precise wavelength where atoms absorb or emit light. When the source moves, the fingerprint slides, toward blue if it approaches, toward red if it recedes. The shift is tiny, but instruments can resolve it with ruthless precision. In practice, astronomers compare whole patterns of lines to reduce ambiguity. Andromeda is moving toward the Milky Way at roughly 100 kilometers per second. The number is large by human standards, yet small compared with the speed of light. It is a drift you could never feel, a closing of distance that still takes billions of years. The two galaxies are gravitationally bound, and the merger will happen in several billion years. Even that prediction carries uncertainty, because dark matter halos and satellite galaxies complicate the dance. That future collision is not a head-on crash of stars because stars are separated by immense gaps. Instead, it is a gravitational dance. Tidal forces stretch disks into long arcs and luminous streams. Gas clouds compress, star formation flares, and the night sky from any surviving planet becomes unrecognizable. The sky would fill with new bands of light, like a second Milky Way poured across the first. Yet the approach does not make the distance feel smaller, because the timescales stay inhuman. Now widen from one galaxy to the small family that contains it. The Milky Way and Andromeda are the two dominant members of the local group. The local group contains roughly 50 galaxies, depending on definitions and new discoveries. The count changes because faint dwarfs hide in the glare of larger hosts, and surveys keep improving. New instruments keep finding dim companions that were always there, just not yet visible to us. Most are dwarves, faint and low mass, orbiting larger hosts like moths around lanterns. Some are satellites of the Milky Way, including the Magellanic Clouds and many ultra-faints. The Magellanic Clouds are bright enough to be naked-eye objects in southern skies, like detached fragments. They are not just decorations, but active systems with their own star-forming regions. The ultra-faints are harder, ghost galaxies held together by dark matter more than by starlight. Those ultra-faints matter because they expose how little light can represent how much mass. Their stars are few, old and spread thin, yet their motions imply deep gravitational wells. In many cases, the visible component is only a tracer, like dust caught in a wind you cannot see. This is one of the cleanest clues that dark matter is not a minor correction. It is the framework that lets such fragile systems persist. Some are satellites of Andromeda, spread through its halo in long, sparse streams. Those streams are not decorative, they are evidence of cannibalism, the slow digestion of smaller systems. A galaxy's halo is a vast dim region where stars and dark matter extend far beyond the bright disk. The local group is full of these relics, as if the past refuses to stay buried. Each stream is a torn page from a smaller galaxy's history. A few are more isolated members, like Triangulum, which is smaller but still substantial. Triangulum's spiral structure is delicate, and its gas-rich disk hints at ongoing star formation. It may be gravitationally entangled with Andromeda, a third partner in a long-term interaction. The group spans a few million light-years, which is already a brutal scale. On a visual map, the galaxies look close, but the empty volume between them dominates the frame, yet it is still a coherent island because gravity binds it against the general expansion. Gravity is the only reason the local group is a thing you can name. Without binding mass, the galaxies would simply ride the universe's expansion away from one another. The local group is a temporary truce between cosmic expansion and gravitational attraction. It is a region where the cosmic stretching loses, at least for now. That truce depends on mass you cannot see. Dark matter dominates the local group's gravitational budget, shaping orbits like an invisible scaffold. The luminous galaxies are only the lit windows in a structure that is mostly dark. When we say bound, we mean the total energy is negative, so escape requires extra energy. In plain terms, the group is a gravitational bowl, and its members are rolling inside it. This is where the central question sharpens again. How does emptiness, plus light speed, plus expansion, turn visibility into permanent unreachability? The local group is the smallest scale where the answer becomes unavoidable. It is the last neighbourhood where nearby still has a technical meaning. Beyond it, the word becomes a psychological comfort, not a physical category. Within this island, distances are still measured in millions of light years. A signal to Andromeda is not a message you send, but a message you entomb. One-way travel time at light speed is 2.5 million years, and nothing can do better. Even if you built a perfect transmitter, the universe would still enforce the delay. The transmission is immediate only in your imagination, not in the receiving sky. Two-way exchange is worse, because conversation requires a reply. A round trip at light speed is about 5 million years, even before anyone decides to answer. Civilizations do not plan in million-year cycles, and institutions do not persist that long. On Earth, even languages drift beyond recognition in a few thousand years, and governments collapse faster. Even religions and empires, which feel ancient, are brief compared with that silence. So communication becomes archaeology, not dialogue. You do not speak to living minds because the delay turns them into historical strata. Even if both sides endure, each reply arrives to a different world. The message is not hello, it is a fossil pressed into the future. If it is understood at all, it will be understood by descendants, not by the sender. This is the tyranny of light speed, and it is not a dramatic limit. It is a simple constant that turns the universe into separated rooms. The rooms can see each other through windows, yet they cannot coordinate across the hallway. The hallway is not a corridor you can walk. It is space-time, and it charges you in years. Every meter of distance is also a slice of delay. Now make the distinction explicit because it will carry the next chapters. Visible is not the same as reachable, and reachability is a physical category. Visibility only means photons arrived, not that matter can follow. A photograph proves light made the trip, not that a ship can. Light is cheap compared with mass, because mass must carry momentum and pay for it. Reachability depends on energy, time, and the shape of space-time between you and the target. Even without expansion, the travel times are so large they erase human meaning. With expansion, the problem becomes structural, because the distance itself can grow. The map changes while you cross it, and the change is not negotiable. You're not simply moving through space. You're moving through a space that evolves. Inside the local group, gravity mostly wins, so expansion is not the main barrier. The main barrier is still the speed limit and the sheer size of the gaps. But beyond the local group, expansion becomes part of the lock. It does not merely slow you down, it can remove the destination from your causal future. The universe can make a place visible, then quietly forbid you from ever arriving. Step outside the local group and the world nearby collapses. The next major galaxy groups and clusters sit tens of millions of light years away. The Virgo cluster is the nearest rich cluster, roughly 50 to 60 million light years distant. In the sky, it is not a single object, but a direction, a region crowded with galaxies. Through a telescope, that region becomes a swarm of faint ovals, each one a separate system. The visuals can tighten here, shifting from one majestic disk to a crowded field of dim ellipses. Galaxies in Virgo overlap in projection, like distant city lights seen through fog. Some are smooth and red, dominated by old stars, while others are blue and messy with new star formation. The cluster looks calm in a still frame, yet it is a gravitational environment of constant interaction. That number is not a larger version of Andromeda's number. It is a different regime, where even light-speed messages become deep time artifacts. A one-way signal to Virgo takes tens of millions of years, and a reply doubles it. By the time an answer returns, continents on Earth would have rearranged, and species would have risen and vanished. The receiver might not even be a receiver anymore, just ruins and geology. Gravity cannot easily bridge these separations on human timescales. Gravitational attraction works, but it works slowly when the distances are enormous. To fall together from tens of millions of light years takes times comparable to the universe's age. Even if two clusters are mutually attracted, the acceleration is gentle, like a whisper across a desert. The pull is real, but it is diluted by distance until it becomes patience. Clusters form where matter was slightly denser in the early universe. In the first few 100,000 years after the Big Bang, tiny fluctuations were imprinted in the cosmic plasma. Those fluctuations appear today as patterns in the cosmic microwave background, a fossil light from the early universe. Over billions of years, gravity amplified those small differences into large structures. The universe's largest buildings began as barely measurable unevenness. But the growth is not something a civilization can ride like a current. The flows are measured in hundreds or thousands of kilometers per second, yet the distances dwarf the motion. A cluster is a city of galaxies, but it is a city built on timescales that ignore individual lives. When you look at a cluster, you are watching a slow collapse that began before Earth formed. The light you receive is the middle of a story that started near the beginning. Between clusters are voids, and voids are not empty in the absolute sense. They are underdense regions where matter is sparse and expansion dominates the long-term flow. The universe's large-scale structure is not a uniform fog, but a network and its gaps. Galaxies trace filaments like dew on spider silk, leaving the interiors of voids dim and thin. The voids are not holes punched in reality, but regions where less grew. Before we reach that network, define what intergalactic space actually contains. Intergalactic space is filled with the intergalactic medium, mostly ionized hydrogen and helium. It is plasma threaded by weak magnetic fields and enriched by traces of heavier elements. Those heavier elements were forged in stars, then expelled by winds and supernovae into the wider dark. In that sense, even the emptiest places are still downstream of stellar violence. The density is so low that everyday language fails. In many regions, you might find only a few atoms per cubic meter, sometimes less. That is emptiness as a measurable quantity, not emptiness as philosophical nothing. A vacuum chamber on Earth is impressive, yet intergalactic space often does better without effort. The difference is that the chamber is engineered, while the void is simply the default. A cubic meter on Earth is a box of air with trillions of molecules. A cubic meter between galaxies can be a near-perfect vacuum by any laboratory standard. Yet it is still a medium, because even rare particles still exist and still interact. Over millions of years, even a few atoms can accumulate into detectable absorption and faint emission. The universe is patient enough that tiny effects become visible. This matters because the universe's horror is not a magical void. It is a physical environment with properties, just stretched beyond intuition. Even near nothingness can carry heat, charge, and momentum over long times. A single proton drifting for 1 billion years still obeys electromagnetism, still bends in a magnetic field. If it meets another particle, even rarely, the collision still conserves energy and momentum. Plasma behaves differently than neutral gas because charges respond to fields. Shocks from galaxies and jets can heat the medium, and radiation can keep it ionized. Ultraviolet light from stars and quasars strips electrons from atoms, maintaining ionization across vast volumes. The intergalactic medium becomes a faint record of cosmic history written in temperature and density. Where it is warmer, something energetic happened, even if the culprit is long gone. Astronomers read that record indirectly. When light from a distant source passes through intergalactic gas, it picks up absorption lines. These lines form a forest of features in spectra, each one a thin slice of matter along the line of sight. Hydrogen leaves a particularly telling signature, because it is everywhere and easy to excite. So even emptiness leaves signatures, subtle but consistent, like fingerprints on glass. The visuals here can shift from blackness to data, rainbow spectra with dark notches, each notch a distance marker. A quasar's light becomes a probe beam, and the void becomes a laboratory sample. The forest is not noise but structure, showing where gas sits between galaxies. Each absorption feature is a reminder that nothing still has composition. The universe does not give us direct access, so it gives us traces. But for travel, the practical meaning is simpler. There is nothing to breathe, nothing to push against, and almost nothing to harvest. A ship crosses an ocean with no refueling ports, where even dust is a rare event. Micrometeoroids exist, but they are not a resource so much as a hazard at high speed. The silence is not poetic, it is logistical, because logistics is what kills dreams first. Now connect this to the earlier chapter's logic about energy and control. In the solar system, you can steal energy from planets through gravity assists. Between galaxies, there are no convenient assist targets, and the distances erase maneuvering options. You cannot slingshot around a void, and you cannot skim a planet that is not there. Your trajectory becomes a commitment, because there are few chances to change your mind. You can accelerate, but you must bring the energy or build it from first principles. You can brake, but braking costs as much as acceleration, and the bill compounds. Even if you imagine fusion or antimatter, the time and mass budgets remain punishing. Relativistic speeds add another tax. Time dilation helps the traveller, but not the universe they return to. The outside world keeps aging, indifferent to your cleverness. So reachability is not only about speed, it is about whether you can arrive with enough control to matter. A flyby at extreme speed is not presence, and presence is what exploration usually implies. To map, to land, to exchange, You must match velocities, and matching velocities is expensive. In intergalactic space, expensive means carrying propellant across millions of years of empty. Even a probe that survives the journey faces a second problem: navigation in a nearly featureless ocean. In the solar system, stars are background and planets are landmarks. Between galaxies, the landmarks are so distant that small errors become huge misses over millions of years. A tiny angular mistake becomes a miss measured in light years, not kilometers. Course correction requires fuel, and fuel is the one resource you cannot borrow from emptiness. Now return to Andromeda, because it is the most emotionally accessible example. People hear that Andromeda is coming toward us and imagine a future meeting. But the actual meeting is billions of years away, and it will not create intimacy. The merger will rearrange star orbits and halos, yet it will not shorten the tyranny of light speed. Even inside one merged system, the distances between stars remain enormous. Even if life exists there, the light we see is from a time before our species. Any signal we send now arrives to a future Andromeda that has evolved for 2.5 million years. The reply, if any, returns to an Earth that has also changed beyond recognition. What would we even mean after that span, and what would they mean on their side? The question is not only technological, but philosophical, because identity has a half-life. So the haunting glow in the sky becomes a lesson. The closest external galaxy is already too far for conversation. The nearest intergalactic neighbour is a time capsule, not a neighbour. It is a reminder that the universe can be visible and still be socially, physically, causally distant. The light is generous, but the distance is final. Now scale outward again, because the local group is not the universe's main unit. Groups and clusters are the next level of organisation, and they are separated by vast emptiness. The separations are not a few million light years, but tens of millions and more. On a map of the nearby universe, these gaps look like blank paper, and the blankness is the story. The ink is galaxies, but the page is void. At that scale, gravity's ability to gather matter is limited by time. It can bind clusters over billions of years, but it cannot make them socially connected. A civilization cannot coordinate across a structure that takes millions of years to exchange a sentence. Even if you could live that long, you would still be talking to the past of the other side. The future you receive is always someone else's history. This is where expansion begins to feel like a second antagonist. Space itself stretches, and the stretching adds distance while you wait. The farther out you look, the more likely it is that reachability is not merely hard, but impossible. Expansion is not an explosion into pre-existing space. It is the growth of space between everything. The ruler you measure with is quietly lengthening in your hands. Even without invoking horizons yet, the logic is already cruel. If the message time is longer than the lifespan of cultures, then contact is functionally zero. If the travel time is longer than the stability of biology, then migration is fantasy. You can imagine machines, archives, or self-repairing probes, but the delay still fractures continuity. What arrives is not you, but a relic of you. So the universe becomes a set of visible islands with no ferries. Light provides a catalogue, but it does not provide access. The catalogue's enormous, and the locked doors are the point. We can name galaxies, classify them, and measure their motions, yet remain barred from participation. We become librarians of a collection we cannot enter. Now introduce the key conceptual split that will drive the next chapter. Visible means information arrived, and reachable means causality can still connect you in practice. In an expanding universe, there are things that remain visible, while becoming forever unreachable. This is the quiet contradiction at the heart of modern cosmology. Seeing does not guarantee touching. The sky can be full, and your future can still be empty of arrivals. The brain resists this because it treats sight as proximity. On Earth, seeing a mountain means you can walk to it given time and effort. In space, seeing a galaxy can mean it is already gone in its own present. The photons are faithful, but they are not current, and the difference matters. What looks like a destination can be only a record. Andromeda is still gravitationally tied to us, so it will not vanish beyond reach. But most galaxies you can see are not tied to you, and expansion keeps pulling them away. The sky becomes a museum whose exhibits cannot be visited, even in principle. We stand in the gallery holding a flashlight, and the beams return with stories we cannot enter. The most distant displays are lit, yet they are behind glass that time will only thicken. Intergalactic space is the ocean with no shores, because there is no continuous surface to cross. There are only islands of gravity and the expanding water between them. The water is not nothing, but it is too thin to help you and too big to ignore. If you drift long enough, the islands do not get closer. The ocean itself can widen. The emptiness is not passive. It participates in the separation. Now set up the transition to the universe's architecture. If the emptiness between galaxies is this severe, then structure itself must be built from emptiness. The next step is to zoom out until galaxies become nodes and voids become the dominant feature. We are not leaving the story of distance behind. We are approaching the design that makes distance unavoidable, the cosmic web. The horror is not only between objects, because emptiness is the structure that holds everything apart. And as we zoom out, the universe stops looking like a scatter of islands and starts looking like a pattern. The pattern is made of light, but it is enforced by darkness, and the spaces between are doing most of the work. Intergalactic space felt like an ocean with no shores. Now we zoom out and learn the ocean has currents, channels, and boundaries. The camera pulls back until individual galaxies stop reading as islands and start reading as grains of light, each one a faint ember suspended in black. The darkness between them thickens into a background that seems featureless at first, like velvet with no texture. Then patterns begin to appear, faint, persistent alignments that refuse to be random, as if the universe has a preferred way to arrange its matter. On the larger scales, the universe is not a simple sprinkle of galaxies across an empty stage, and it never was. It is a cosmic web of filaments and nodes, separated by vast voids that swallow most of the volume and hide most of the story. The web is not a metaphor chosen for poetry alone, because it is measurable in surveys and reproducible in simulations. It is a geometry traced by matter and by the gravity that matter creates, an architecture you can quantify, not merely admire. Filaments are long, thread-like concentrations of matter, sometimes hundreds of millions of light-years in length, and they can be tens of millions of light-years thick. In wide-field maps they look like luminous strands, but most of their mass is not luminous and never will be. They contain galaxies, hot gas, and the dominant mass we infer as dark matter, an invisible backbone that shapes everything else while refusing to announce itself. When we visualize a filament, imagine a dim river of galaxies flowing through blackness, with bright spirals and quieter ellipticals marking the current. Spiral disks tilt at different angles, ellipticals glow like embers, and faint dwarf galaxies cluster around larger hosts like sparks around a coal. Between those galaxies lies gas so thin it would qualify as a vacuum by Earth standards, yet it still matters because it fills the volume. It is heated by shocks and gravity, and it can glow in X-rays or ultraviolet when compressed, leaving a ghostly outline of where matter is being funneled. Nodes are intersections where filaments meet, and they are the web's densest junctions, the places where the flow lines converge. They host groups and clusters where gravity has gathered matter into compact energetic environments that can dominate their neighborhood. In these nodes, galaxies are crowded enough to interact repeatedly, not as brief impacts, but as long tidal negotiations. They can be stripped of gas, distorted by tides, and stirred by encounters that are slow-motion collisions on cosmic timescales. In a rich cluster, the space between galaxies is not empty either, and the emptiness is an illusion that optical light encourages. It is filled with intracluster plasma at tens of millions of degrees, so hot that atoms are fully ionized and electrons roam freely. That plasma shines in X-rays, revealing the depth of the gravitational well and the violence of assembly. The heat is not a detail. It is a signature of how brutally matter fell inward, converting gravitational potential energy into thermal motion. Voids are the opposite structure, and their scale is easy to underestimate because they do not announce their edges with bright landmarks. They are enormous underdense regions where galaxies are rare, and expansion has room to stretch with less gravitational resistance. Some voids span tens of millions of light-years, while the largest can approach a few 100 million, swallowing volumes that could contain thousands of Milky Ways. Inside them, the universe feels like a missing chapter, as if matter simply forgot to show up, and no one filed a correction. This pattern looks eerie because it resembles biology and foam, and our brains are trained to see intention in branching shapes. It is not alive, but it is shaped by the same rule that shapes many natural patterns, from river deltas to crack networks. Small imbalances grow when feedback amplifies them, and the amplification does not need a designer or a plan. Gravity is enough, patient, cumulative, and indifferent to scale. The web answers a question we have been circling since Chapter 1, even when we did not name it directly. Distance is not just between objects, like a ruler laid across emptiness, because the emptiness itself has structure. Distance is built into the architecture, because matter and expansion organize space into regions that connect and regions that separate. The web is the universe's way of turning geometry into fate. We only know the web exists because we learned to map depth, not just direction, and that was a historical triumph of technique. A sky full of points becomes a three-dimensional distribution when you add distance, and distance is the hard part. Without distance, a filament can masquerade as a chance alignment, a trick of perspective. With distance, it becomes a structure you can measure, model, and test, and the illusion collapses into a physical fact. Astronomers do this with redshift surveys, which are the modern equivalent of charting an ocean by sounding its depth, one measurement at a time. They measure how spectral lines shift, then convert that shift into distance using cosmology and a model of expansion. The technique sounds straightforward, yet every step carries assumptions about how the universe expands and how matter influences that expansion. Even the ruler is built from theory, and that is why the map is never just a photograph. A spectrum is a barcode of light, with lines produced by atoms absorbing or emitting specific wavelengths as electrons change energy levels. Hydrogen, calcium, oxygen, each leaves a recognizable fingerprint, and those fingerprints survive across billions of light years. When a galaxy is moving away, or when space itself stretches, those lines slide toward longer wavelengths. That sliding is the redshift, and it is one of astronomy's most powerful rulers because it ties light to motion and history. Redshift is not only motion through space, like a siren changing pitch as it passes, and that analogy breaks at cosmic distances. It is also the stretching of space itself, which lengthens wavelengths as light travels through an expanding universe. The longer the journey, the more the wave is stretched by the expansion that occurred during its flight, and the light arrives carrying that accumulated change. In that sense, redshift is a record of time as much as it is a measure of distance. In the nearby universe, redshift behaves almost like a simple speedometer, and Hubble's linear relation feels reassuringly clean. Farther out, the relationship becomes more subtle, because expansion has changed over cosmic history, and acceleration reshapes the conversion. Cosmology supplies the translation, using parameters that describe matter density, dark energy, and the geometry of space. The map is therefore a collaboration between observation and theory, each correcting the other when the fit begins to drift. A survey collects millions of galaxy spectra and positions, often over years of patient observation and careful calibration. Telescopes sweep the sky with multi-fiber instruments that can take thousands of spectra at once, each fiber placed like a needle on a target. Each spectrum is a tiny story of a galaxy's stars and gas, but the survey's purpose is statistical rather than intimate. The result is a map where filaments emerge from correlations, not from any single dramatic object. On screen, the data becomes a cloud of points in 3 dimensions, and the camera glides through it like a slow dive. Rotate it, and the cloud stops looking like noise, because the eye catches continuity across distance. Strands appear, then knots, then empty cavities that feel too clean to be accidental, as if someone erased regions with a careful hand. The human eye is good at finding structure, but the web is not a trick of perception, and it survives rigorous tests. The web is not drawn by hand, and it is not a pattern imposed after the fact to satisfy our hunger for meaning. It appears when you compute clustering, power spectra, and correlation functions across huge volumes, and those tools are deliberately blind to aesthetics. These are methods that treat the galaxy distribution like a physical field, the way meteorologists treat pressure and temperature. The mathematics asks a simple question. Compared to randomness, what separations occur too often? Those statistics describe how likely galaxies are to be separated by a given distance, averaged over space and over millions of objects. The excess probability reveals structure beyond chance, and it does so in a way that can be compared across surveys and epochs. If the universe were a random sprinkle, the correlation would flatten and the map would lose its teeth. Instead, it rises on certain scales, reflecting the web's preferential separations and its stubborn tendency to cluster. There is also a signature scale imprinted from the early universe, a faint ripple called baryon acoustic oscillations, and it acts like a standard yardstick. It shows up as a subtle bump in the correlation function, like an echo in the distribution that refuses to fade. It is not a new topic here so much as a reminder that the web is not only present tense. Even the web's statistics carry fossils of primordial physics, preserved as a spacing preference in the cosmic pattern. Even then, the map is not perfect because our measurements are not made from outside the universe with a god's eye geometry. Peculiar velocities distort redshift space, smearing clusters into fingers along our line of sight, because internal motions add to the redshift. In plots, dense clusters stretch into spikes pointing toward us, as if the cluster is trying to reach the observer. The effect is geometric, not physical, but it is telling because it reveals hidden motion. That distortion is a warning and a tool, and the two roles are inseparable in practice. It reminds us that distance is inferred, not directly measured, and inference can be fooled by velocity. It also reveals how gravity moves matter, because the same velocities that confuse the map encode the growth of structure. When interpreted carefully, the smearing becomes a measurement of dynamics, turning an error into a signal. The web's existence forces a deeper origin story because filaments are too coherent to be late accidents painted onto a mature universe. They are scars from the universe's first moments, amplified and sharpened by gravity over immense time. If you want to understand the web, you have to ask what the universe looked like before any galaxy existed, before any star had a name. The answer is almost blank, and that almost changes everything. Go back to the early universe, when everything was hot, dense, and nearly uniform, a plasma of particles and radiation coupled tightly together. Nearly uniform is the key phrase, because uniformity is stability, and stability is boring in a gravitational universe. A perfectly smooth universe would expand and cool without ever developing texture, without ever breaking into places. The fact that we have texture means the early universe had imperfections, and those imperfections survived. If it had been perfectly smooth, gravity would have had nothing to amplify, and the future would be empty of complexity. A smooth universe stays smooth, and nothing intricate forms, not even the first stars, because there are no wells to fall into. Gravity cannot create contrast from nothing, because it needs a gradient to pull along and a difference to exaggerate. Structure formation is therefore a story of initial conditions, and the web is the long consequence of tiny asymmetries. Instead, there were tiny fluctuations in density, present everywhere like faint static under a signal, and they were astonishingly small. They were not mountains and valleys, not even hills and dips, but parts per 100,000 differences in an otherwise uniform sea. Yet in a universe governed by gravity, small differences are not harmless, because they accumulate and they self-reinforce. They are seeds, and the future is built from seeds. The unsettling claim is that those differences may be quantum in origin, which sounds like a category error when you first hear it. Random microscopic fluctuations were imprinted into reality's initial conditions, then expanded into cosmic scale patterns that later guided galaxies. It is difficult to accept because quantum randomness feels private and local, like a jitter that cannot matter. Here it becomes public and universal, written across the entire sky. Quantum fields cannot be perfectly still, even in what we call a vacuum, because uncertainty is built into their behavior. They fluctuate, producing temporary variations in energy and density, and those variations are as real as the field itself. In laboratory physics, such fluctuations are usually fleeting, and they average out into nothing you can point to. They do not leave permanent marks on the macroscopic world, because the world is too large and too warm. In ordinary life, such fluctuations vanish into noise, and the world stays stable because countless jitters cancel out. In the early universe, something happened that refused to let them disappear, and that refusal is the pivot. Instead of being erased, they were promoted, frozen in place by rapid expansion. The universe did not merely contain fluctuations, it preserved them, stretched them, and handed them to gravity as instructions. Inflation is the leading idea for that something, and it was proposed in the early 1980s to solve puzzles about the Big Bang's initial conditions. It proposes a brief era of extremely rapid expansion, far faster than later cosmic growth, occurring in a fraction of a second. During inflation, space itself expands at an extraordinary rate, smoothing some features while magnifying others. The result is counterintuitive. The universe becomes more uniform overall, yet the tiny fluctuations become cosmically large and dynamically important. Inflation takes tiny regions and stretches them to astronomical size, like a pattern printed on a balloon as it inflates, except the balloon is space itself. It turns subatomic irregularities into seeds spanning light years and beyond, then locks them in as classical perturbations. The fluctuations stop being quantum-sized and become classical, meaning they can act like real density variations with definite amplitudes. When inflation ends, the universe is still hot and dense, but it now contains a faint blueprint that gravity can read. This is the accessible horror of the origin story because it is not about monsters or malice, but about scale and amplification. Small causes become huge consequences because the universe scaled them up without asking permission and without leaving a receipt. A random twitch in a quantum field becomes, billions of years later, a supercluster boundary or a void wall. The web is therefore a monument to amplification, a reminder that size does not imply intention. The web is not a design added later, and it is not a decorative layer on top of an otherwise smooth cosmos. It is the amplified memory of randomness, frozen into a pattern that gravity could read and then deepen. When we map filaments, we are reading a message from the earliest instance, and we are reading it indirectly. The message is not written in words, it is written in statistics, in distributions, in the stubborn way matter refuses to be uniform. We see a fossil of those early conditions in the cosmic microwave background, the afterglow of the Big Bang that fills the sky. Its temperature anisotropies trace the same initial unevenness, at the level of tens of microkelvin, which is almost nothing, and yet everything. On screen, the CMB looks like a mottled sphere, blue and red patches scattered across the sky in delicate speckle. Those patches are not weather. They are density differences encoded in radiation, a thermal map of a young universe. The CMB is not the web itself, and it does not show galaxies or filaments because those structures had not formed yet. It is the blueprint, a snapshot from about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to form neutral atoms. At that moment, photons stopped scattering constantly and began to travel freely, turning the cosmos transparent. The CMB is therefore a photograph of the universe becoming visible, a last scattering surface that still surrounds us. From that blueprint, gravity becomes the sculptor, and time becomes the chisel, working slowly but without pause. Overdense regions pull in more matter, and their pull grows as they gain mass, deepening the potential wells. The process is slow at first, because the contrasts are tiny, and radiation once resisted collapse. Then it accelerates, because gravity is non-linear, and small advantages compound into dominance. Underdense regions do the opposite, and their behavior is just as important for the final geometry. Matter flows out, leaving voids emptier over time, as if space is evacuating itself and forgetting what used to be there. The evacuation is not a force pushing outward, and that distinction matters for clarity. It is the absence of inward pull, allowing expansion to dominate and allowing matter to drift away along gradients. This feedback is simple and merciless, and it does not require complex chemistry or life to get started. Where there is slightly more, gravity makes even more, and the difference sharpens into a filament or a node. Where there is slightly less, it drains, and the region becomes quieter and emptier as time passes. A universe with gravity will always exaggerate its own imperfections, given enough time and enough room. Over billions of years, the universe becomes foam-like, with a geometry that resembles bubbles pressed together in slow motion. Filaments and sheets surround expanding cavities of emptiness, and nodes sit where several walls meet, glowing with crowded galaxies. In simulations, you can watch this happen as if it were a time-lapse film, with matter streaming along invisible slopes. The early universe begins as faint noise, then condenses into a network that looks inevitable once it appears. Those simulations are not artistic guesses, and their history matters because they changed cosmology's confidence. In the late 20th century, as computing power grew, cosmologists began evolving dark matter particles forward in time under gravity, starting from CMB-like initial conditions. When they did, the web emerged naturally, long before the simulations included detailed galaxy physics or feedback from stars. That was a revelation. The large-scale structure is primarily gravitational, and the luminous universe is a decoration on a deeper scaffold. Dark matter leads much of this process, because it does not collide or radiate in the way normal matter does, and it does not lose energy by shining. It does not emit light, but it clumps early, providing gravitational wells for gas and galaxies to fall into later. Because it interacts weakly, it can begin collapsing while the early universe is still dominated by radiation pressure that resists baryonic collapse. Dark matter is therefore the first architect of the Webb scaffolding, laying down channels before the lights turn on. Baryonic matter follows the dark scaffolding, and it does so reluctantly at first, slowed by pressure and by its own ability to heat. Gas falls into potential wells, heats, cools, forms stars, and lights the Webb's outlines, turning invisible structure into visible landmarks. Heating comes from compression and shocks, while cooling comes from radiation emitted by atoms and ions as electrons drop between energy states. Where cooling is efficient, gas can settle and form stars. Where it is not, the gas remains diffuse, glowing faintly and shaping the environment without building many galaxies. So the bright galaxies are not the structure's full mass, and they are not even the dominant component, which is the quiet twist. They are tracer dye in a river whose main current is invisible, marking where the flow is strongest. When you look at a filament in optical light, you're seeing the rare luminous peaks, not the full distribution. The dark matter extends beyond them, smoother and more massive, guiding their arrangement like a hidden mold. This is where the central question sharpens again, because the Webb is not merely a map of where things are. Emptiness is not a background, and it is not a passive stage waiting for actors. Emptiness is the dominant volume, and it controls reachability because it is where expansion faces the least resistance. The universe's separations are not just distances, they are the consequence of living in a cosmos where most space contains almost nothing to slow expansion down. Filaments feel like roads, but they are not built for travelers, and they do not promise connectivity in the human sense. They are gravitational channels that guide matter over cosmic time, not highways designed for crossing, and their lanes are millions of light years wide. Matter drifts along them because the potential landscape slopes that way, like water finding the lowest path. The drift is slow, and the distances are brutal, and the word path is only an analogy. A galaxy does not choose its path, and it does not need propulsion because gravity does the steering. It drifts along gradients in the gravitational field, pulled by mass it cannot see directly and cannot negotiate with. The motion is typically hundreds of kilometers per second, which sounds fast until you compare it to the scale and the patience required. At that pace, crossing even a small fraction of a supercluster takes longer than civilizations have existed, and longer than most species survive. When we say galaxies are in a supercluster, we often imagine a stable community, like a city of galaxies with clear borders. The Webb forces a colder definition, because many memberships are temporary alignments in a flow rather than permanent residency. Some galaxies are falling in, others are passing by, and some are already being carried away by expansion. The word cluster can mislead, because it suggests permanence, and the universe rarely offers permanence on these scales. To make that real, place the Milky Way inside its larger address, and let the map keep expanding until the local becomes a dot. We are in a region called Laniakea, identified and named in 2014, and the name means immense heaven, which is accurate and slightly cruel. On a visualization, Laniakea is not a neat sphere. It is a basin-shaped region defined by motion, with edges that follow the flow of galaxies like contour lines in a gravitational landscape. Laniakea is not just a cluster catalogue entry, and it is not just a boundary drawn because it looks nice on a plot. It was defined by mapping motions of thousands of galaxies, not only their positions, and that choice is the point. Positions can deceive, because two galaxies can look close and still be moving apart in the long run. Motion reveals what gravity is doing right now, and it reveals where the currents truly run. Those motions include peculiar velocities, which are the deviations from the smooth Hubble expansion caused by local gravity and local structure. In an expanding universe, galaxies generally recede with distance, and that recession is described by the Hubble-Lemaitre law, a relationship built from observation and refined over decades. Peculiar velocities are the extra components layered on top: sideways drifts, infalls, and streaming motions along filaments. They are the universe's weather, superimposed on the general climate of expansion, and they are messy in exactly the way real dynamics should be. To measure them, astronomers need distances independent of redshift, which is harder than it sounds and historically took generations of work. They compare redshift-inferred distance to distance from standard candles, or scaling relations, and both require careful calibration. Standard candles include objects like Cepheid variables and certain supernovae, whose intrinsic brightness can be estimated from their light curves. Scaling relations include methods like the Tully, Fisher relation for spirals and the fundamental plane for ellipticals, which tie observable properties to distance with scatter that must be managed. The difference between these distance estimates reveals a galaxy's motion relative to the expansion, and that difference is small compared to the full recession. That motion points toward mass concentrations, even when the mass is partly dark and partly hidden behind dust. It is a gravitational arrow, pointing not to a single object, but to a gradient in the mass distribution that extends across the map. When you collect enough arrows, the noise averages down and the flow becomes legible, like a wind field emerging from many drifting leaves. When you plot many such vectors, patterns appear, and the map begins to resemble a topographic field rather than a simple scatter plot. Flow lines trace basins of attraction, like water draining across a landscape after rain, and the analogy is more than poetic. Some boundaries are sharp, where flows diverge decisively, and others are fuzzy where the gravitational tug-of-war is nearly balanced. The fuzziness is not failure, it is physics, because gravity competes across distance, and the competition has gradients. Laniakea was defined as one such basin, and the definition is intentionally dynamical rather than purely geometric. It is the region whose galaxies flow toward a common gravitational destination, even if they are separated by enormous distances. The boundary is where the flow changes direction, like a ridgeline separating watersheds on Earth, and that ridge is drawn by motion. This is a different way to think about cosmic structure, because it is about trajectories rather than labels, and about present tense rather than eternal membership. That destination is associated with the Great Attractor, a name that can sound like science fiction if you do not hear the caveats. It is not a single object, but a direction of enhanced mass in the nearby universe, including clusters and superclusters that collectively tilt the gravitational field. The phrase, Great Attractor, reflects our perspective as observers being pulled, not a special entity exerting magic. It is a region where the mass distribution is lopsided enough to bend the local flow. The Great Attractor sits behind the Milky Way's disk in our sky, near what astronomers call the zone of avoidance, and that phrase is literal. Dust and stars obscure direct views in visible light, so its influence was inferred from motion and from surveys that can pierce the dust at other wavelengths. This is a reminder that even in precision cosmology, there are blind spots that the galaxy itself imposes. We reconstruct what we cannot see by watching how other things move, and the reconstruction is always an act of inference. This is a callback to earlier mapping limits, and it is part of the chapter's mood of being trapped inside the system we measure. We live inside structures we cannot see cleanly, and we reconstruct them by their gravitational fingerprints rather than direct images. The universe does not offer an external vantage point, and it never will. Our maps are always made from within the maze, and the maze includes our own galaxy's dust. Laniakea's scale is meant to break intuition, and it succeeds almost immediately even when you know the numbers. It spans about 520 million light-years across and contains on the order of 100,000 galaxies, each with its own history of star formation and collision. Those numbers are not just large. They are cognitively hostile, because they exceed the scales our minds evolved to navigate, and they refuse to become familiar. Say the number slowly and it still fails to land, because the unit itself is a trap that hides what it implies. 500 million light-years is not a distance you imagine. It is a timescale for light, and light is the fastest messenger the universe allows, the hard limit on influence. When you say light-year, you're already talking about the time it takes causality to cross space, and time is the real barrier. Even if you could move at light speed, crossing Laniakea takes longer than complex life has existed on Earth, and that comparison is not rhetorical. Complex multicellular life is only a few 100 million years old, depending on where you draw the line between simple and complex. The supercluster is so wide that biology's entire recent history fits inside a single traversal, and the traveller arrives to a changed cosmos. At any realistic speed, it is not travel in the human sense, and it is not even exploration in the way we usually mean it. It is a geological epoch with engines, and the destination changes while you are en route, because the universe evolves. Stars are born and die, galaxies merge, and the expansion of space subtly alters the map and the separations. The universe does not hold still for voyagers, and it does not pause for comprehension. The psychological horror is not only bigness, and it is not only the emptiness between points, though both are relentless. It is that the mind cannot hold the hierarchy for long without dropping pieces, like trying to juggle scales that do not fit in memory. Galaxy, group, cluster, supercluster, web, and still more. Each step multiplies the scale until meaning starts to leak away. We can say the words, but we cannot inhabit them, and that gap is where unease grows. Laniakea also corrects a common misconception, and the correction is important for the theme of separation and fate. A supercluster is not necessarily gravitationally bound forever, and it may not remain coherent as a single object. The term supercluster can describe a present arrangement rather than a permanent entity with a guaranteed future. In an accelerating universe, the future is not obligated to preserve today's patterns, even if the patterns look stable now. Some superclusters are transient patterns in the cosmic flow, like eddies in a river that will eventually unwind and disappear downstream. Expansion competes with gravity, and the boundary between bound and unbound is subtle, depending on mass, geometry, and the universe's acceleration. A region can be flowing inward today and still fail to remain a single unit in the far future, because the background expansion keeps gaining leverage. The web is dynamic, and its categories are sometimes provisional, which is unsettling in its own quiet way. A basin of attraction is a present tense description, not a promise carved into space-time, and that distinction matters for how we interpret maps. It tells you how matter is moving now, not a guarantee of eternal membership or eternal togetherness. Boundaries can shift as structures evolve, and as cosmic expansion changes the balance of forces, and the map redraws itself slowly. Even the language of belonging becomes suspect on these scales, because belonging implies permanence and the cosmos offers trends, not vows. This matters for the documentary's theme of permanent separation, because it reframes what together even means in an expanding universe. Even structures that look like communities can dissolve as the universe expands, and the dissolution can be gradual enough to hide in plain sight. A galaxy can share a filament with others and still be destined for isolation, carried away by expansion beyond any practical horizon. The web can connect places geometrically while separating them causally, and that contradiction is the sting. The cosmic web is therefore not a static skeleton, and it is not a frozen lattice hung in space like a decoration. It is a living map of motion, with filaments feeding nodes and voids growing larger, and the feeding changes the web's thickness. In simulations, you can watch filaments thin as they drain into clusters, while voids swell like slow balloons that never stop inflating. The web is a process, and the process has a direction, even if it has no intention. The web also reframes what it means to be unreachable, because reachability is not only about speed, and not only about propulsion. In a filament, matter can drift toward nodes, and signals have a denser environment to traverse, with more intervening structure. Across voids, the drift is starved, and the separation grows more absolute, because there is little mass to pull trajectories together. A void is not just empty space. It is a region where the universe's expansion is less resisted by gravity, and that resistance matters. Voids are not empty holes, but they are close enough to empty to dominate the future, and that is their power. Their low density means little gravity to pull things back or to slow the stretching of space, so they widen as time passes. Inside a void, galaxies are few and far between, often small and isolated, with less fuel delivered by cosmic flows. The night sky from such a galaxy would be poorer, with fewer bright neighbours to hint at the larger web, and fewer reminders that anything lies beyond. As voids expand, they push matter into their edges, not by pressure but by differential gravity and the geometry of the potential field. The edges become filaments and walls, and the interiors become quieter still, with less interaction and less replenishment. This is why the web looks like foam when you step back far enough. The bubbles are the voids, and the bright lines are the compressed boundaries where matter accumulates, like ridges around an expanding emptiness. So the web is built by evacuation, and that phrasing is more literal than it sounds when you follow the flows, The universe sorts itself by draining matter from some regions and piling it into others, and the sorting is statistical but real. The draining is slow, but it is relentless, and it is guided by the initial blueprint laid down in the earliest moments. Over time, the contrast between filament and void increases, sharpening the universe's separations and making the emptiness more dominant. This sorting takes billions of years, yet it began with quantum randomness, which is the story's spine and its unsettling elegance. The chain from micro to macro is not a slogan. It is a causal ladder, where each rung depends on the last and none can be skipped. Quantum fluctuations become inflationary perturbations, which become density variations, which become gravitational flows, which become the web we map today, and the chain ends in the sky we see. It is also a reminder that our location is not special, even if it feels like a centre from our viewpoint and our maps. The Milky Way is one tracer point in one filamentary region within one basin, and the basin itself is not the whole story. Our galaxy's light is not a beacon of centrality. It is one more pixel in a picture too large to frame, and the picture does not privilege the pixel. Our local filament connects to larger structures, and those connect to others, and the connections are real in a geometric sense. Yet the travel times make them meaningless, and that is the chapter's quiet sting, because it turns connection into irony. Connectivity without access is a kind of cosmic joke told without laughter. The universe can be networked and still be isolating, because the network is scaled for gravity, not for minds. If you imagine the web as a road system, the speed of light is the speed limit, and the limit is absolute and indifferent. The map can be connected and still be unusable, because the distances are not scaled for machines or civilizations. Even at light speed, the web is a prison of time, and time is the wall you cannot climb. You can point to a destination, but you cannot arrive within any familiar horizon, and the horizon keeps shifting. Even communication is strained, and it becomes stranger the farther you look, because delay changes meaning. A signal crossing hundreds of millions of light years arrives as a relic, and a reply doubles the burial time, turning exchange into archaeology. By the time a conversation completes one exchange, the civilizations involved, if they exist at all, may have transformed beyond recognition or vanished. The web permits messaging, but it does not permit dialogue, and the difference is everything. So the web is a catalogue of places we can name but cannot visit, and naming is not the same as knowing. It is a network that does not grant access, only perspective, and perspective is a thin comfort. We can trace the filaments, measure their statistics, and infer their mass, even when the mass is dark. Yet we remain pinned to one small region, watching the rest through ancient light that cannot be hurried. This is the chapter's escalation, and it is meant to shift the scale of confinement without changing the logic. We are no longer trapped by the gap between stars or between galaxies, because those gaps were only the beginning. We are trapped by the universe's layout, by the way matter and emptiness are arranged, and by how expansion exploits that arrangement. The prison is not a wall, it is a geometry drawn in the distribution of almost nothing, and the layout is mostly nothing, which is the detail that changes the emotional centre when you let it settle. Filaments are the exception, and they are thin compared to the volumes they outline, like lines on a map that hide the size of the blank paper. Voids are the rule, and the rule is what expansion amplifies, because emptiness offers less gravitational resistance. As time passes, the voids claim more of the universe's attention, because they claim more of its space, and they do it quietly. Now the transition that changes the emotional centre, and it does so with a simple reversal that feels almost unfair. If filaments are the roads, then voids are the true rulers. They are missing chunks of universe. A void is not merely a place without landmarks, and it is not simply a gap between brighter things. It is a region where the web withdraws, where the gravitational conversation grows quiet and the flows thin out. The few galaxies inside are like distant boats on a dark sea, separated by stretches of black that offer no intermediate steps and no easy routes. The emptiness is not decorative, it is structural, and it is what the universe is mostly made of. In the next chapter, we enter the voids directly, and we do it without the comfort of bright nodes or crowded skies. We ask what it means for most of reality to be almost empty, and still expanding away, and still shaping everything that remains. We ask how isolation changes when emptiness is not an absence, but the dominant form of space itself, and we ask what that dominance implies for the future of connection. You're not trapped on Earth. You're trapped inside a distance problem so vast that even light can't solve it fast enough. Chapter 5 showed the cosmic web as structure built from evacuation, where filaments are thin and voids dominate volume. Chapter 6 enters the most unsettling implication of that architecture. Some regions are not merely far, they are missing. A void is not a hole punched into reality, and it is not a clean absence of physics. A void is an underdense region where matter exists but is drastically reduced compared with the cosmic average. That word average matters, because expectation is statistical, built from surveys that count galaxies per volume across many lines of sight. We compare one region's counts to the mean density measured across many directions and distances, then ask how unusual the deficit really is. We correct for what telescopes can detect, we correct for what they miss, and we still find places that come up nearly blank. Visually, a void is first seen as a silence in a map, an empty bubble inside a lattice of points. In a 3D redshift survey, galaxies become coordinates, and the web becomes a fog of luminous markers. Then a cavity appears, not as darkness on the sky, but as a volume where the dots simply stop. The eye keeps searching for a boundary, because the brain expects walls, yet the border is statistical rather than solid. The emptiness is a measurement, not a shadow. Voids expand because gravity has less to pull inward, so the background expansion wins more easily. Matter drains out of underdense regions toward denser filaments and walls, following the gradient of the gravitational potential. In simple terms, particles roll downhill in the gravitational landscape, and voids are the hilltops. Over time, the contrast sharpens, and the void becomes emptier in relative terms even if it is never truly empty. The cosmic web is not only where matter is, it is where matter is not. Absence is part of the structure. The physics is subtle because expansion is not a force pushing matter outward like wind. Space itself stretches, and gravity competes with that stretching by trying to pull mass together. In a dense cluster, gravity can slow local expansion, and in extreme cases it can reverse it into collapse. In a void, there is less mass to resist the stretch, so the region dilates more quickly than average. The result is a kind of cosmic sorting, where density peaks grow denser and density troughs grow emptier. If you could watch the universe in accelerated time, voids would look like bubbles swelling in a rising foam. Filaments would thin into strands, then thicken at their intersections, where clusters gather like knots. Sheets would flex and fold, not as rigid plates, but as gently curving walls of galaxies. The motion would be slow enough to feel geological, yet decisive enough to redraw the map. The web sharpens not by adding matter, but by redistributing what already exists. Psychologically, voids are anti-places, because they remove the landmarks the brain uses to feel oriented. Distance without intermediate objects becomes distance without narrative, a corridor with no doors and no corners. In a filament, you can at least point from galaxy to galaxy, and pretend there is a route. In a void, the route is an idea with no steps, and the steps are what make distance tolerable. The horror is not darkness, it is the loss of reference, an emptiness that refuses to become a story. Even our language betrays us, because we talk about crossing a void as if it were a gap between islands. The reality is closer to crossing an ocean with no stars, no coastline, and no way to know whether you drifted off course. Navigation depends on feedback, and feedback depends on nearby targets that can be measured and revisited. A void offers almost none of that, so the mind experiences it as pure separation. It is distance stripped of texture. The emblem is the Boötes void, discovered in 1981 as surveys began to map galaxies in 3 dimensions. It was not found by staring at a blank patch of sky, because the sky is always full of foreground stars. It was found by measuring redshifts, turning points of light into distances, then noticing a volume that should have contained far more. The void is roughly 330 million light-years across, large enough to swallow thousands of Milky Ways by volume, yet it contains only a few dozen galaxies, where thousands would be expected at the mean density. To understand why that was shocking, remember what redshift surveys were becoming in the late 20th century. Before the 1970s, the universe was mapped mostly as a flat projection, with distance guessed from brightness and morphology. Then spectroscopy became routine, and redshift became a standard ruler of recession, at least statistically. Each galaxy spectrum carried a barcode of shifted lines, and that shift implied how far space was stretching between us and it. When enough of those measurements were assembled, The universe stopped being a star field and became a volume. In that volume, Botas was not just sparse, it was anomalously sparse. The void's interior was not completely empty, and that detail matters for the science and the mood. A few galaxies live there, often small, gas-rich and relatively isolated, like outposts that never joined a city. Their existence proves the void is not a forbidden zone, only a region where growth was starved. The question becomes why the starvation is so extreme in that particular place. Expected does not mean predicted by a single theory in isolation, and it does not mean every region must match the mean. Expected means that if you sample many comparable volumes, most contain a similar order of magnitude of galaxies. The expectation comes from the observed galaxy luminosity function and clustering statistics, folded through the selection limits of the survey. If you can only see bright galaxies at that distance, you adjust the expected counts accordingly. Even after those corrections, Botas remained an extreme underdensity, a place where the cosmic web thins toward near nothing. The luminosity function is a quiet piece of machinery behind that word expected. It tells you how many galaxies exist at each brightness, and it is steep, meaning faint galaxies are far more common than bright ones. A survey that misses faint galaxies will undercount everywhere, so astronomers model that incompleteness carefully. They also model how galaxies cluster, because galaxies are not sprinkled randomly like dust. Clustering statistics predict how much variation you should see from region to region, even in a uniform universe. So when Botas comes up nearly blank, the claim is not, there are no galaxies, but the deficit is too large to be ordinary. It is a statement about probability, not a statement about absolute absence. In practice, astronomers ask how many standard deviations the underdensity represents. Given the survey's volume and selection, they test whether the result survives different magnitude cuts and different sky masks. The void keeps reappearing, which is why it became an emblem. The Botas void also reveals how we learn about emptiness by looking for what is missing. We do not measure voids the way we measure planets, by direct outline and direct edges. We infer void boundaries from where galaxies and groups stop appearing in redshift space, and we model the boundary as a surface of low density. We check for biases, because dust, instrument limits, and incomplete sky coverage can fake gaps. The void survives those checks, which makes it a real feature of the large-scale distribution. Redshift space itself adds a complication that makes the inference more delicate. Galaxies have their own motions on top of the Hubble flow, and those peculiar velocities distort the map. Clusters can look stretched into fingers pointing toward us, because internal velocities add to redshift. Voids can look slightly squashed or elongated depending on surrounding flows. So void-finding algorithms must distinguish real underdensities from distortions created by motion. Physically, the void still contains dark matter, gas, and radiation fields, but at reduced density. The intergalactic medium threads through it, and the cosmic microwave background still fills it. There are still particles per cubic meter, still magnetic fields, still the faint pressure of photons, yet the gravitational wells are shallow, so structure grows slowly and interactions are rare. A galaxy inside a void is not only isolated from neighbours, it is isolated from the flows that feed galaxies elsewhere. The dark matter point is crucial, because galaxies are only the visible frosting on a much larger mass distribution. In the standard picture, dark matter provides the scaffolding where gas can cool and form stars. In a void, that scaffolding is thinner, and the halos that do form are typically lower mass. Lower mass halos struggle to hold onto gas against heating from ultraviolet background radiation. The result is fewer luminous galaxies, and those that exist can remain chemically primitive for longer. Even the gas between galaxies behaves differently in an underdense region. The intergalactic medium is ionized and tenuous, and its temperature and density reflect a balance of expansion, shocks, and radiation. In filaments, gas can be compressed and heated, and it can flow toward nodes where clusters grow. In voids, gas expands and cools, and it can remain too diffuse to condense efficiently. The void is not merely empty of galaxies, it is empty of the conditions that make galaxies common. This is where the central question tightens, because emptiness is not just scenery. Emptiness changes what can ever be reached, because it reduces gravitational binding and lets expansion separate regions more cleanly. In dense nodes, gravity can keep a neighborhood coherent against the Hubble flow, at least for a long time. In voids, the Hubble flow has room to dominate, and the separation becomes the default outcome. The universe is designed to separate, and voids are the design made visible. Think of gravity as a kind of social force in the cosmos, one that creates neighborhoods. A cluster is a neighborhood where galaxies exchange gas, merge, and orbit a shared center of mass. A filament is a highway of infill where matter drifts toward denser intersections. A void is the opposite, a region where the traffic flows outward, away from the center toward the walls. If you are born inside it, the universe is quietly pushing your surroundings apart. The mind tries to turn the cosmic web into a roadmap, because roads imply travel and travel implies agency. Voids break that coping strategy, because they are not roads between places. They are the absence of places, and absence cannot be navigated the way a network can. Even if you could cross the void, you would cross a region with almost no intermediate targets for correction or resupply. The distance becomes pure time delay, and time delay becomes pure disconnection. Imagine the visuals: a camera drifting through a 3D simulation, where galaxies are rendered as pale sparks. In a filament, sparks pass by like a slow meteor shower, with occasional clusters blazing like cities. Then the camera enters the void, and the sparks thin until minutes pass with nothing but faint background glow. The cosmic microwave background is everywhere, yet it offers no parallax, no texture, no hint of progress. The emptiness becomes a soundless pressure, now escalate from missing matter to impossible structure, because the same maps that reveal voids also reveal walls. Filaments and sheets can align into vast complexes that look like megastructures on the larger scales. The question becomes whether these are real coherent objects or artifacts of how we sample the universe. The tension is not only size, it is whether our statistical tools are being pushed past their safe limits. A void is a deficit we can test repeatedly, while a wall can be a pattern that appears only when the data are thin. Introduce the cosmological principle gently, because it is the quiet rule behind most of modern cosmology. On sufficiently large scales, the universe should look roughly uniform and isotropic, with no preferred direction and no special location. This does not mean every region is the same, because the web is real, and clustering is real. It means that when you average over large enough volumes, the fluctuations should wash out. The principle is not philosophical comfort, it is an empirical assumption tested by surveys and the cosmic microwave background. Historically, the principle grew out of a hard lesson in humility. Astronomy repeatedly demoted Earth, then the Sun, then the Milky Way from the center of things. By the 20th century, it became natural to assume we're not in a special cosmic address. That assumption turned into a quantitative framework, because it makes the equations of cosmology solvable and predictive. Yet it is always an approximation, and approximations become fragile at the edges of data. So extremely large claimed structures create debate because they appear to violate the scale where homogeneity should emerge. If a structure is too large, it suggests the universe has coherent features beyond the expected correlation length. That could mean our models are incomplete, or it could mean our detection method is biased. It could also mean the structure is not a single object, but a chain of alignments we are naming as one. The argument is about where pattern ends and projection begins. There is also a subtle point about what structure means at these scales. A galaxy cluster is a gravitationally bound object, and its membership is physically meaningful. A supercluster can be partly bound and partly dispersing, and its edges are already ambiguous. A great wall is often not bound at all, but a region of enhanced density stretched across the map. So the debate is not only about size, but about whether the word object still applies. The most famous recent example is the Hercules, Corona Borealis Great Wall, a claimed structure estimated up to about 10 billion light-years in extent. That number is not a measured diameter like a planet's, and it is not a wall you can trace in a continuous survey. It is inferred from clustering of gamma-ray bursts, brief flashes that can be seen across enormous distances. GRBs are rare, so the map is sparse, and sparsity makes patterns easier to overinterpret. On screen, the data look almost comically minimal compared with a galaxy survey. Instead of millions of points, you see a few hundred, scattered across the celestial sphere. Then a redshift slice is applied, and only a subset remains, floating like pins on a translucent globe. In that subset, a region seems crowded, and the mind instantly draws a boundary around it. The wall is born in that moment, an outline sketched by human pattern recognition. Explain the inference clearly, because this is where observation strains. Researchers take GRB positions and redshifts, then look for statistical clustering in a particular redshift range. If more bursts appear in one region of the sky than expected by chance, it suggests an underlying overdensity. The implied overdensity could be a supercluster complex, or a set of connected filaments, or a selection artifact. The result depends on sample size, sky exposure, and how the detection thresholds vary across instruments. Gamma-ray bursts are not a single kind of event, which complicates their use as tracers. Some are linked to the collapse of massive stars and those track star formation in certain environments. Others are linked to compact object mergers, and those follow different timescales and host populations. Their brightness distribution is broad, and their detectability depends on how the burst is oriented and how its afterglow behaves. When the tracer is heterogeneous, the map inherits that complexity. Selection effects are not an insult, they are the default problem of astronomy. GRBs are detected by satellites with uneven sky coverage and evolving sensitivity. Redshifts are not measured for every burst, and follow-up depends on weather, telescope time, and brightness. Dust and foreground contamination change what can be localized and what can be spectroscopically confirmed. A clustering signal can grow from these biases if they correlate with direction or depth. Even the sky itself is not equally observable, because the Milky Way blocks and confuses. Near the galactic plane, dust absorbs optical light, and dense star fields complicate localization. Satellites also have operational constraints, and their exposure varies with pointing strategy and orbit. So the random sample is never perfectly random, and the corrections are never perfectly complete. The Wall claim lives in that imperfect space. Statistics also punish us when events are rare, because small number fluctuations look like structure. If you have only a few hundred points, random clumps are guaranteed somewhere on the sky. The question is whether the clump is more significant than the look elsewhere effect, the penalty for searching many possible regions and scales. Cosmologists ask whether the claimed wall remains unlikely after accounting for that search. The debate is not about whether patterns exist, it is about whether the pattern is robust. This is why significance thresholds become more than academic. A 2 sigma hint can feel persuasive in a dramatic visualization, yet it can vanish when the sample doubles. A 5 sigma claim sounds definitive, yet it can still hide systematic bias if the model of selection is wrong. The universe does not sign its structures with labels, so we rely on probability. Probability, in turn, depends on assumptions that must be defended. Even if the clustering is real, the word wall can mislead, because it implies a contiguous object. Large-scale structure is often a network of filaments and sheets, with voids threaded through it. A wall may be a percolating complex, not a single slab of matter. The boundary between one structure and another can be a naming choice rather than a physical discontinuity. Our language turns gradients into objects because objects are easier to think about. There is a deeper visual trap here, because a sparse data set encourages the brain to connect dots. When the points are dense, the web's geometry is obvious and redundant, and false connections are harder to sustain. When the points are few, any alignment looks intentional, like constellations drawn on a star chart. The Great Wall claim sits uncomfortably close to that cognitive edge. It may be real, but it must fight the suspicion that it is a cosmic constellation. This is the edge where our map depends on faint biased signals, and the universe stops offering redundancy. Galaxy redshift surveys can map millions of galaxies, but only to certain depths and with certain selection functions. GRBs reach farther, but they are sparse and heterogeneous. Quasars and absorption forests add other tracers, but each tracer has its own biases. The farther we look, the more we stitch together different datasets with different failure modes. At closer distances, a wall can be checked by multiple methods at once. You can count galaxies directly, measure their velocities, and trace gas with absorption lines. At extreme distances, you may have only a handful of beacons, each with its own uncertainties. The map becomes a collage, and the seams matter. Cosmology is still possible, but it becomes more conditional, more dependent on careful modelling. So the tension becomes a choice between two unsettling possibilities. The universe may be simpler than it looks, and the Great Walls may dissolve under better statistics. Or the universe may be more fractured, with coherent features on scales that challenge our assumptions. Either way, the human mind loses a comfort. In one case, we learn that our perception of structure is a mirage built from sampling. In the other, we learn that the universe's separations are organized by patterns we did not expect. Tie this back to voids, because voids and walls are two sides of the same mechanism. Voids grow as matter drains to filaments, and filaments thicken as voids evacuate. The web sharpens with time, and sharpening increases contrast between crowded and empty regions. That contrast affects reachability, because dense regions can remain gravitationally coherent, while empty regions expand more freely. The universe does not separate evenly, it separates by geography. In simulations, this geography emerges from tiny early fluctuations that were almost perfectly uniform. The initial density field had variations at the level of parts in 100,000, and gravity amplified them over billions of years. Regions that began slightly underdense became voids, and regions that began slightly overdense became filaments and clusters. The later map looks dramatic, yet it is the slow unfolding of a nearly smooth beginning. That contrast between origin and outcome is part of the unease. Now bring the psychological framing forward again, because this chapter is the climax. A void is distance without landmarks, and a claimed wall is a landmark too large to trust. One removes orientation by erasing structure, the other removes orientation by overwhelming scale. Both force the same admission that our mental map is not built for cosmic cartography. We can compute these scales, but we cannot inhabit them. The Buddha's void is a clean kind of terror because it is a measurable absence. It is a region where the expected inventory of galaxies fails, and the failure persists across methods. It is a reminder that most of the universe's volume is not filled with destinations. It is filled with near nothing, and near nothing still takes hundreds of millions of years for light to cross. The emptiness is not a shortcut, it is a delay with no scenery. To picture that crossing, imagine a beam of light leaving one edge of the void when early mammals were just beginning to diversify on Earth. That beam would still be travelling through the underdense interior, long after continents shifted and ice ages came and went. The void does not merely separate places, it separates eras. When we say 330 million light-years, we're also saying 330 million years of waiting. The Great Wall claims are a different terror, because they threaten the rule that makes cosmology possible. If the universe is homogeneous on large scales, then we can model expansion with a small set of parameters. If there are coherent structures on scales of billions of light-years, then the averaging scale is larger than we thought. That would not instantly break relativity, but it would complicate the translation from redshift to distance. It would mean our map is less like a smooth atlas and more like a patchwork. Keep the cosmological principle grounded, because it is often misunderstood as saying the universe is featureless. The principle allows filaments, clusters, and voids, because those are local departures from the mean. It says that beyond some scale, those departures average out so no direction is special. The debate is about the scale at which that averaging becomes reliable. The debate is also about whether our tracers are sampling that scale fairly. There is an observational parallel in the cosmic microwave background, which appears astonishingly uniform. Its tiny temperature variations provide a snapshot of early density fluctuations, and they support the idea of large-scale isotropy. Yet the microwave background is a surface of last scattering, not a direct map of late-time structure. Late-time structure grows by gravity, and it can look more dramatic than the early imprint. The principle survives, but it is continuously tested. This is why cosmologists argue about walls with unusual intensity. The argument is not only about a headline number, it is about whether the foundational approximation still holds. If the approximation fails, then many distance inferences become more model-dependent. If the approximation holds, then the walls are likely statistical percolations or selection artifacts. Either way, the farther we look, the more we depend on inference rather than direct census. Now connect the chapter to the documentary's hook, because the hook is not only about size. You're trapped inside a distance problem, and voids are the purest expression of that trap. A void is a region where even the cosmic web offers fewer stepping stones for matter and meaning. Light can cross it, but it crosses as a thin message with no possibility of return on human timescales. A ship can cross it only as a thought experiment, because there is nothing to interact with and no way to correct the journey cheaply. Even observation becomes a kind of confinement, because our instruments are limited by photons and by patience. A galaxy survey is a census of what emits or absorbs light above a threshold. In a void, there is less to emit, so the map becomes uncertain by default. In the deep universe, everything is faint, so the map becomes biased toward the brightest and most extreme objects. Our picture of the largest structures is therefore built from the rarest beacons. The practical details of that bias are easy to forget when the visuals look clean. Telescopes have limiting magnitudes, and exposure time buys depth only slowly. Spectroscopy is expensive, and redshift measurement can fail when lines are weak or obscured. Survey footprints avoid bright stars and the Milky Way, carving holes into the sky coverage. Every correction is a model, and every model carries assumptions. Gamma-ray bursts are the extreme case, because they are visible across most of the observable universe. They are also not steady lighthouses, but brief explosions with complex progenitors. Their rate depends on star formation history, metallicity, and galaxy type, which vary with environment. If GRBs prefer certain environments, then their clustering may not trace mass uniformly. The tracer may be biased, and biased tracers can mimic walls. A burst can also be missed for mundane reasons, and mundane reasons matter at the edge of cosmology. A satellite might be looking elsewhere, or the burst might be too short to trigger a threshold. The afterglow might fade before ground telescopes can respond, leaving no redshift. The sample you end up with is not all bursts, but bursts that were detected, localized, and followed up. That chain of filters shapes the map, so the chapter's climax is not a single object, but a confrontation with epistemology. We are mapping a universe we cannot step outside, using signals that arrive late and unevenly. We are extracting structure from incomplete samples, correcting for biases we can estimate but never fully eliminate. We are asking whether the largest patterns are real, while knowing that our methods can manufacture patterns. The horror is not ignorance, it is partial knowledge that looks complete. Return to Buddha's one more time, because it anchors the emotional arc in something solid. A 330 million light-year cavity is already beyond the brain's ability to treat as a place. It is a span longer than the time complex life has existed on Earth, measured in light travel alone. It is a region where the universe's average inventory fails, and the failure is the point. It tells us that the cosmos is not a continuous field of destinations, but a foam of presence and absence, and that foam is not static, which makes the absence feel even stranger. The void's interior continues to expand, and the galaxies within it drift away from each other faster than the cosmic mean. The walls around it continue to accrete matter, becoming more prominent in contrast. The universe is not simply large, it is actively sorting itself into emptier and denser regions. The map is a process, not a snapshot. Then pivot back to walls, because walls force the opposite discomfort. If a wall is real at the claimed scale, then the universe holds coherent features across a significant fraction of the observable volume. That would mean our local patch is embedded in patterns too large to survey cleanly. It would mean that what we call average might be more local than we admit. It would mean that the map's background assumptions are part of the story, not invisible scaffolding. Hold both possibilities in tension, because the documentary's tone is exploratory, not declarative. The Great Wall may shrink with better data, or fracture into smaller connected components. It may also persist as a real statistical anomaly, forcing revisions in how we describe large-scale structure. In either case, the lesson is the same for reachability. The universe's geometry is not built for access, and our knowledge is mediated by delay. Now make the separation theme explicit, because this is Chapter 6 and it must land hard. Voids show that most of the universe's volume contains almost nothing, so most directions offer no nearby targets. Walls show that the universe can arrange what remains into patterns too large to verify easily. Together they imply a cosmos where emptiness dominates travel and uncertainty dominates maps. The prison is not a cage, it is a layout, an architecture that turns motion into waiting. This is also where the earlier promise about visible but unreachable returns with force. A void can be visible as a deficit, yet it offers no path to interaction beyond passive observation. A wall can be visible as a statistical excess, yet its components may already be causally drifting away. The farther out the structure, the more expansion matters, and the more reachability decouples from visibility. Seeing becomes a weaker and weaker guarantee of connection. Ask the uncomfortable question that hides inside the data. What does it mean to know a place you can never visit? We can assign coordinates, redshifts, and confidence intervals, and we can simulate plausible histories. yet the information arrives as ancient light, and the object has already changed by the time we describe it. The map is always late, and the universe does not wait for our conclusions. In a cosmos shaped by delay, certainty is always provisional. So the chapter ends by tightening the documentary's central question into a boundary condition. How does emptiness, combined with a light speed and expansion, turn most of reality into something permanently unreachable? Voids remove stepping stones and amplify separation, while expansion stretches the gaps that remain. Walls tempt us with structure, then remind us that structure does not equal access. The universe can show you its architecture and still deny you entry. Transition to the final chapter must be unavoidable, because the climax demands a limit. Light has a finite speed, the universe has a finite age, and expansion changes what can ever be contacted. The next chapter goes to the horizon itself, where the map ends not in darkness but in physics. We move from voids and walls to the ultimate limits: light's finite speed, the early universe, an expansion that turns distance into a one-way separation. You're not trapped on Earth. You're trapped inside a distance problem so vast that even light can't solve it fast enough. Across this series, distance stopped being a line on a map and became a delay in causality, a lag between an event and its consequences. The Moon kept orbiting for 1.3 seconds after Earth vanished, because gravity updates at sea and the change cannot arrive early. Sunlight arrived 8 minutes late, because even warmth is a message carried by photons through vacuum. Voyager whispered from the dark because radio is light in costume and the weight is built in. The Milky Way became provinces that cannot synchronize, because a light year is a year of separation, not a convenient unit. The cosmic web became a foam of filaments and voids, because emptiness dominates volume and expansion exploits emptiness. Now the story reaches its hard limit. The universe does not only separate places, it separates eras, then it separates futures. Light is time delay, and time delay is the only way we ever see, because seeing is receiving a signal that has already travelled. Every photon is a receipt from the past, stamped with the travel time it survived and the interactions it avoided. When a telescope gathers light, it is not collecting now, it is collecting then, bundled into wavelengths and arrival times that must be decoded. The deeper we look, the younger the universe appears, because we are looking back along the light cone and down the slope of cosmic history. A galaxy 10 billion light-years away is not 10 billion years old to our eyes. It is 10 billion years younger than the version of that region that exists today. Observation is archaeology performed at sea, and the excavation tool is patience, calibration, and a ruthless accounting of noise. We subtract glare from our own atmosphere, then from our own dust, then from our own instruments. We learn to trust a faint smudge only after we prove it is not a defect, not a cosmic ray, not a statistical mirage. That is why the James Webb Space Telescope matters in this final chapter. JWST is not a bigger eye aimed at farther places in the present. It is a machine tuned to catch older and older light, stretched and weakened by expansion. In orbit near the Sun, Earth L2 point, it unfolds like a metallic flower, then hides behind a layered sun shield the size of a tennis court. Its mirrors cool, because infrared astronomy is a fight against your own heat. A warm telescope glows, and that glow can drown the very photons you're trying to hear. JWST's deep fields reveal galaxies more than 13 billion light-years away, packed into images that look like black velvet sprinkled with embers. Those points of light are not distant neighbours as they are now. They are the same regions as they were when the universe was less than 1 billion years old. The visual is almost cruel in its simplicity. A few pixels brighten, a faint arc appears, a reddish dot refuses to vanish under longer exposures. Then spectroscopy splits that dot into a pattern, and the pattern carries the signature of distance. The implication is not just that the universe is old, the implication is that distance forces us to meet everything as a child. Even the biggest telescope cannot show a mature early galaxy, because maturity happens after the light we receive already left. In those early epochs, galaxies were assembling fast, fed by cold streams of gas and punctuated by violent mergers. Massive stars lived briefly, burned hot, and died in supernovae that seeded heavier elements. The universe was learning chemistry in real time, because carbon, oxygen, and iron had to be manufactured before planets could ever be ordinary. The light arrives redshifted, because expansion stretches wavelengths during the journey, turning tight ripples into long swells. What left as ultraviolet and visible starlight is pulled into infrared by the time it reaches us. JWST is built for that shift, because the early universe is not only far, it is literally moved into a different colour by the universe's growth. Redshift is not a cosmetic tint. It is a record of how much the universe expanded while the photon was in flight, encoded as a ratio of wavelengths. Astronomers write it as Z, where higher Z means the scale factor of the universe was smaller. In plain terms, the universe has grown since the light began its trip, and the light carries the stretch marks. That record is also a clock, but it is a complicated clock. Converting redshift into time depends on the universe's expansion history, which depends on matter, radiation, and dark energy. Distance ties to history, and history ties to a changing conversion between redshift and time. So JWST's farthest galaxies are not simply far away. They are evidence that the observable universe is a time machine with a strict speed limit. We can only read the archive at the pace the archive can arrive. There is a second constraint hidden inside that sentence. As you go farther back, the available light becomes rarer and more fragile. Photons are diluted by expansion, and their energies drop as wavelengths lengthen. Then the archive runs into a wall. Beyond a certain point, there is no starlight to collect, not because nothing existed, but because the universe was once opaque. Early on, the cosmos was a hot plasma of electrons and protons, and photons could not travel freely. Light scattered constantly, like fog that never clears, because charged particles grab photons and throw them back. In that plasma, the mean free path of a photon was tiny, and space behaved like the interior of a star. Temperature and density was so high that atoms could not stay intact. Any would-be hydrogen atom was immediately torn apart by energetic radiation. At about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to form neutral hydrogen. This is recombination, and it made space transparent for the first time. Photons stopped bouncing and began streaming, and those photons still fill the sky. The word recombination is historical, and it hides a subtlety. There was no earlier era of stable atoms to recombine into because the universe began too hot. Yet the term remained, a reminder that science carries its own archaeology of language. When neutral hydrogen formed, the universe also entered a new phase of structure growth. Without photons constantly pushing on charged particles, matter could begin to clump more efficiently under gravity. The seeds were already there as tiny density fluctuations, and transparency let those seeds evolve. We call that relic radiation the cosmic microwave background. It is the afterglow of the moment the universe became visible, cooled and stretched into microwaves by expansion. It is not light from stars, it is light from the universe itself when the universe was the source. On screen, the CMB is often shown as a mottled globe, coloured in false blues and reds. Those colours represent temperature differences of mere tens of microkelvin, variations so small they sound like rounding errors. Yet those slight ripples are the blueprint of everything that later formed. The CMB is also astonishingly uniform, which is its own kind of mystery. It tells us the early universe was smooth to about 1 part in 100,000. That smoothness is why the sky looks calm, and it is also why galaxies took time to emerge. The CMB is an observational wall because it is the earliest light that can reach us. Beyond it, there is no earlier electromagnetic picture to take, because the plasma was a barrier. We can infer earlier times through neutrinos, gravitational waves, and theory, but not by ordinary photons. This is where the documentary's mapping theme resolves. We have been building maps from inside the maze, correcting for dust, bias, and selection. Here the maze ends in physics, and no calibration can push past it. Even our best instruments cannot cheat scattering. A bigger mirror collects more photons, but it cannot collect photons that never had a free path. The universe itself sets the start date of visibility, then stamps it across the entire sky. Yet even the CMB is not the final limit on reachability. It is the limit on what we can see from the past. The next limit is about what we can ever touch in the future. Cosmology uses the word horizon in more than one way, and that overlap can hide the danger. The particle horizon is about how far we can see, given the universe's finite age and light speed. It is the boundary of the observable past, and it grows as time passes. If you wait longer, more time passes for light to travel, and more distant regions can finally send you their first photons. That is intuitive, and it feels hopeful, like a frontier that slowly opens. The particle horizon is the universe saying, not yet, rather than never. The event horizon is different, and it is colder. It is the boundary of what can ever be contacted, even with infinite patience. It is a limit on causal influence, not a limit on current visibility. In an accelerating universe, there exists a cosmic event horizon at roughly 16 billion light-years. Regions beyond it can still be visible in ancient light, yet light emitted now from those regions will never reach us. The universe can show you a place, and still forbid any future conversation. This is the promised contradiction from earlier chapters. Visible does not mean reachable, because reachability depends on the future behavior of expansion, not only on the past path of a photon. A photograph can arrive, and a reply can still be impossible. To make that intuitive, imagine sending a signal today. The signal moves at sea through space, yet space itself expands during the trip, stretching the path beneath it. If the expansion rate effectively outruns the signal beyond some distance, the gap grows faster than the message can close. This is not the same as galaxies moving through space faster than light. In general relativity, recession is the growth of the metric, the scaling of distances between co-moving points. Locally, no object outruns a nearby beam of light, and special relativity keeps its authority. Dark energy is the name we give to the observed acceleration of cosmic expansion. It is not a push through space like wind. It is the behavior of space itself, making the scale of the universe grow faster over time. Historically, this acceleration was not expected. In the late 1990s, supernova surveys used Type Ia explosions as standardizable candles, comparing how bright they appeared to how redshifted they were. The result implied distant supernovae were dimmer than a decelerating universe would predict, and the simplest explanation was acceleration. In everyday terms, the road is lengthening while you drive, and the lengthening accelerates. For nearby destinations, you still arrive because gravity binds local structures, and the stretching is weak. For far enough destinations, the road grows faster than your maximum speed, and arrival becomes impossible. This is not a failure of engineering. It is a boundary condition of the geometry we live in. Earlier chapters offered an escape hatch, because the mind always reaches for one. Warp drives and faster-than-light shortcuts appear as a loophole, because they promise to cheat the speed limit by moving space. Yet every known version demands exotic negative energy, stability control, and radiation constraints that remain unresolved. Even as speculation, they do not remove the horizon problem, because the horizon is a global feature of expansion. A horizon is not a fence sitting somewhere in space. It is a statement about world lines, about which trajectories can ever intersect. You cannot aim at the event horizon and break it, because it is defined by the total future of the universe, so the event horizon is not a wall you could reach and drill through. It is a boundary in spacetime that defines which futures can share causes. It is the universe drawing a circle around us, then slowly tightening it. The horror is that this circle is not static. Accelerating expansion means more and more galaxies will cross beyond the event horizon over time. Their light already on the way can still arrive for a while, but new light will not. Imagine watching a distant city at night through a telescope. For years you receive its old glow and the skyline seems stable. Then, without any explosion or catastrophe, updates stop arriving and the city becomes a fossil image. The universe becomes a shrinking archive. Each year, some fraction of the sky's information becomes a one-time delivery, never to be updated again. The photons you receive are not a live feed. They are delayed postcards, and the post office eventually closes. Gravity fights back locally, and that is why we still have a neighborhood. The local group is bound, and the Milky Way and Andromeda are on a collision course. In a few billion years, they will likely merge into a single remnant galaxy, while nearby dwarfs orbit within the same gravitational island. On the visual side, this is not a gentle meeting. Tidal tails stretch like luminous ribbons, gas clouds compress, and bursts of star formation flare in blue clusters. The central black holes drift, then spiral inward, and the merged galaxy settles into a smoother, older shape. That bound remnant is the future observer's entire accessible cosmos. Beyond it, galaxy groups that are not bound to us will recede, dim, and redshift away. Over long times, they will slip beyond the event horizon, and become causally disconnected forever. Even before they vanish completely, they become harder to interpret. Their spectra slide into wavelengths where detectors must be larger and colder, and their surface brightness drops as their light spreads over an expanding canvas. The sky does not go dark all at once, it thins. For a future civilization inside that remnant, the night sky will not look like ours. The rich extragalactic background will fade because most galaxies will become too redshifted and too faint to detect. The cosmic web will not be a visible network, it will be an erased memory. This is a strange reversal of our own era. We live at a time when the universe is still legible, when large-scale structure can be surveyed and the Hubble flow can be measured. That legibility is temporary, and it is not guaranteed by any principle of fairness. Even the CMB will not stay loud. As expansion continues, the CMB's wavelength stretches further, its temperature drops, and its photons become harder to measure. Eventually it becomes so cold and so long wavelength that it blends into noise and local foregrounds. A future observer might build radio antennas the size of planets and still struggle, because the signal's contrast against local sources keeps falling. The CMB does not disappear, but it becomes practically inaccessible, like a whisper under a storm. That future observer may have no evidence that other galaxies ever existed. Without visible galaxies and without a measurable CMB, the simplest model would be a lone island in an eternal static emptiness. The Big Bang could become an unprovable hypothesis, not because it was wrong, but because the evidence left. What would such a civilization conclude about cosmic history? Would they invent an origin story that fits their sky, then defend it as obvious? Would they suspect missing data? Or would the concept of missing data never occur? This is the climax of the central question. Emptiness provides the volume, light speed provides the delay, and acceleration provides the permanent cutoff. Isolation is not temporary and not psychological. It is built into the universe's geometry. We began with a simple thought experiment about Earth vanishing and the Moon not knowing yet. We end with the same rule applied to everything, scaled up until it becomes fate. Causality has a speed limit, and expansion decides which distances become one way. So what is the most horrifying distance in space? It is not only a number of light years, because numbers can be written down without being felt. It is the distance to the horizon where the universe erases itself, where places remain visible only as old light, then stop updating, then stop being reachable. The final image is not a monster in the dark. It is the night sky as a shrinking archive where each arriving photon is a farewell from a place we can never touch. The universe is not designed to be explored by travelers. It is designed to separate, and it separates more cleanly as time goes on. We began by learning that distance is not a number on a map. It is a time delay that amputates cause from effect. Sunlight is 8 minutes old, the Moon's gravity would keep it secret for a heartbeat, and every command to a probe is really a prediction. Then the borders kept receding, from the heliopause to the inferred Oort cloud, from the nearest stars to a Milky Way fractured into provinces that can never share the same now. Beyond our galaxy, the local group becomes an island, the cosmic web becomes our address, and the voids, vast, underwritten spaces, quietly dominate the universe's volume. And at the far edge of observation, the horizon turns the whole sky into archaeology, while dark energy accelerates the separation, making visible and reachable diverge forever. Along the way, we watched how knowledge itself becomes an inference engine, built from dust-veiled maps, redshift barcodes, Cepheid rhythms, supernova, and the CMB's microkelvin scars. We questioned the seductive loophole of warp travel, and found it waiting behind exotic energy, stability problems, and hazards that read like nature's fine print. We weighed the reality of walls and the temptation to see patterns in sparse traces, and returned to the cosmological principle, not as comfort but as a disciplined way to admit uncertainty. We also met the deepest limit, the one no rocket equation can negotiate, where finite light speed, finite cosmic age, and accelerating expansion draw a boundary around what can ever be contacted. Past that boundary, galaxies may still shine into our telescopes, yet their futures have already slipped outside any possible conversation. The most unsettling revelation is not emptiness, but design. Gravity gathers, expansion stretches, and the universe sorts itself into things that can touch and things that never will. Voids expand faster, matter drains into filaments, and the web sharpens like a fracture line. even as our own neighbourhood remains bound and grows more alone. The archive of the cosmos keeps arriving, photon by photon, but the catalogue of destinations shrinks as the event horizon quietly edits the future. In the far distance, what we call now is already a relic, and what we call near is only a promise measured in light travel time. Even the unanswered questions sharpen the theme rather than soften it. Dark energy's true nature remains hidden, and if it changes, the horizon story could change with it. But the present geometry already imposes permanent losses. Other messengers, neutrinos, primordial gravitational waves, may someday whisper from before the CMB wall, yet they will still obey causality's accounting. And a far future civilization, born after the sky has thinned of galaxies and the CMB has redshifted into silence, may find the Big Bang not disproven but unprovable, like a history whose documents have burned. The horror, then, is not a monster in the dark. It is the slow, lawful disappearance of evidence, destinations, and shared time. In that sense, the universe's greatest distance is not measured in light years, but in the growing gap between what exists and what can ever be reached. We can map the web, name our basin of attraction, and estimate the age of the first light. Yet the cosmos remains mostly a set of coordinates we will never visit. The farther we look, the more we realize that out there is not a place awaiting arrival, but a past that can only be watched. And every chapter of our journey has been a different way of saying the same thing, that isolation is not an accident of technology, it is a property of space-time. There is still wonder inside that constraint, but it is a colder wonder, one that asks for humility instead of conquest. The heliosphere is a bubble, the galaxy is a city of strangers, the intergalactic ocean has no shores, and the horizon is a door that only opens inward. When we speak about exploring the universe, we're often describing exploration of light, not of locations, and the distinction matters, because the universe is not merely large, it is actively becoming more separated, and the separation is written into the rules. So let's return to the question that opened this film, the one that sounded like a threat. How does emptiness, light speed, and cosmic expansion turn most of reality into something permanently unreachable? It happens because the universe enforces a maximum speed for influence, and then stretches the space between influences faster than they can cross. The result is a cosmos where contact is not limited by patience or engineering alone, but by horizons, boundaries that decide without malice which regions can ever share a cause and effect relationship. You're not trapped on Earth, not exactly, but you're trapped inside a causality budget, and the universe spends it with ruthless efficiency. Most of what exists will never be visited. Most of what we see is already gone in time, and some of what we can still see is already beyond rescue. The terror is not that we are small, it is that the universe is built to make together a temporary condition. And if that sounds bleak, it is also clarifying because it tells us what is rare. What is rare is not matter, but connection, not distance, but shared present tense. For a little while, in one gravitationally bound pocket of the cosmic web, atoms learn to look back along the light and ask where it came from. The universe may be designed to separate, yet here we are, briefly able to reconstruct its history from delayed photons, to infer invisible scaffolds, and to name the edges of the knowable. That may be the only defiance available to creatures who cannot outrun light. So if you want a final thought to carry out of this darkness, let it be this. The most horrifying distances in space are not the ones we cannot imagine. They are the ones that quietly erase the possibility of ever meeting, ever confirming, ever returning. The universe does not need walls to imprison us, because expansion turns empty space into the wall, and time turns every view into a goodbye. If this story unsettled you, keep looking anyway, because every measurement we make is a small act of connection, before the horizon makes even the evidence unreachable. The real horror was never simply what's out there, it was what space-time refuses to let us touch, no matter how long we wait. Emptiness slows nothing, light speed caps everything, and expansion pulls the rest away, until visible becomes permanently different from reachable. In an accelerating universe, the farthest places are not just far, they are departing, and the light that proves they exist is already a message from the past. The last cold truth is this: space isn't a frontier, it's a separation machine, and we are living in the brief interval before it finishes its work. So stay curious, support the instruments and missions that read this fading archive, and remember that understanding is how we reach what we can't touch.